My friends, welcome, welcome, welcome. The stars are finally right for the buffer overflow walkthrough, my friends. The stars are finally right. We are finally here. This has been much requested, and I have just decided that I really need to do justice to this and give us a good baseline of understanding before we get into this stuff, because these are the deep magics, folks. These are the dark arts, I know plenty of pen testers who find binary exploitation completely unapproachable, and so my goal today is to de-obfuscate that for you. De-obfuscate binary exploitation as much as possible. Yeah, I think I just turned it down on 31D. Yeah, so so we got to a step. So that's what we're doing today. Today those of you who don't know, my name is Alhazred. Thank you. We have so many new viewers today, I guess from InfoSec Prep. Thank you so much for coming. If you guys are OSCP hopefuls, this is you're in the right freaking place, my friends. You are in the right place. My name is Alhazred, and I am here to teach you the dark arts, the black magics. Cthulhu himself is shivering in his slimy grave with the thoughts of the things that we're going to cover today. These are intense. Yes, it will be a VOD. You'll be able to access it on Twitch, and I'm going to post it on YouTube at some point. We're going deep into it today, boys. Now, normally, I'm a new streamer. I've been only doing this for about a month. We've been generally doing blind CTFs, like hack the box, try hack me, and that sort of thing. But today we're not doing that. Today, this is all binary exploitation. We're starting from the ground up. You don't need to know who's the owl already. Gifting, you madman, you lunatic, you psychopath. You already with 3 bonus subs. Welcome to the Alhazred team, my friends. Thank you so much. You guys have been so kind. Purple Fox, thank you for the 100 bits. You should be hyped. Everyone should be so fucking hyped right now. You should be excited because I am about to show you the dark magic, okay? The real dark magic. Like, a lot of times we get on Hack the Box, we guess a password to fucking WordPress or something. Those aren't the dark magics, okay? These are the dark magics, and we're gonna talk about them today. We got so much to go over. So what are we doing first? What are we doing first? Oh my goodness, 1,000 bits this time. D. Williams, thank you so much. Thank you so much, my friend. Thanks for supporting the stream. You guys are just so nice, so good to me. I cannot. How about starting to lower your pull-ups? Yeah, I know. I do need to. We're gonna get there. We're gonna get there. So what are we doing first? So we're not gonna jump right into the demo, my boys. AG Zor, thank you for the subscription, my friend. Welcome to the Alhazred team. We're not gonna jump right into the to the demo today, boys. Not right in. Believe me, we're gonna get there. Before you know it, we're gonna be in a demo. The vast majority of the stream will be spent in the demo. But we're gonna start off with some PowerPoint slides. I know. PowerPoint dance game. Get your dance games in chat. Get them all out of your system, okay? PowerPoint dance game. Okay, I get it. But I need exactly. You just checked out. I just lost half the viewers. Okay, I just lost half the viewers. Jazeel, thank you for the follow, my friend. Cthulhu Fatagan, good to have you around. But we have to look, my friends. It's real easy to not understand this stuff, and I know a lot of pen testers who don't really understand it. They claim that they do, but they don't really understand it. We need to establish a baseline of understanding, and PowerPoint gives me a medium that is helpful to do that. So we're going to start off with some slides. We're going to go through them fast. I promise. We're not going to get super in deep with the slides, and then. Yeah, fundamentals are key, especially here, Barters. Fundamentals are key. It is crucial that you not only understand the process that I'm going to show you in the demo, but that you understand the theory behind it. Okay, it is absolutely crucial. Cyber Bonus, thank you so much for the follow, my friend. Cthulhu Fatagan. We're going to talk about bad characters. We're going to talk about them. We're going to talk about bad characters. We're going to talk about... This is going to be extremely OSCP-like. Okay? Extremely OSCP-esque. Obviously, I can't do exactly what you're going to see on the OSCP exam. This is a real-world vulnerability in a real piece of software that I am going to fuzz, I am going to debug, and I am going to exploit right in front of you. And I'm gonna explain everything. Nightmare! You psychopath! This man comes in here every single day, and every time I stream, this guy comes in here, and he just like, we're in the hype train right now. We're at level 3 complete. Guys, I'm not even hacking you right now. Like, if you want me to, I'm not even hacking you to give me hype. I'm not even doing this. He's just, this madman is just fucking giving me subs. This guy's a psychopath. He's out of control. Someone get control of this man. He's completely out of control. Anyway, thank you for the 100 bits, D. Williams. Thank you so much. So this vulnerability is about as close to OSCP as you're gonna see in a real world vulnerability. I could have done something a little bit closer, but it would have been in a piece of software that's intentionally vulnerable to teach you OSCP like concepts. But I wanted to do it in a real piece of software, so you know this is for once I didn't want it to be a CTF. I wanted it to be a real piece of software. So this is but I promise you, we're gonna go over everything that is covered in OSCP. Every single aspect of the OSCP buffer overflow will be covered today. I'm going to point out the most common things that are done wrong in the OSCP buffer overflow so you can avoid it on your OSCP exam. And I swear to God, for those of you who are OSCP hopefuls, who are going to take OSCP soon, coming up on your exam pretty soon, I promise you that if you watch this stream today, you understand what I'm teaching you, and you follow the process that I'm going to give you, I promise you that those 25 points on the OSCP exam will be free. Those are free points, my friends. Absolutely free. Are you ready to hop into it? Are you ready? Are you ready, chat, to get into this? Are you ready to get into this? I have to know you're ready. I have to know you're prepared. Is your body prepared? You guys should be at least at a half chub right now, okay? You should be sexually aroused by what we're going to be covering, okay? You absolutely should be into this. We're getting into it. We're getting into it. Oh, by the way, let's start off with I'll just start a Stream Raiders battle. I forgot up until now. For those of you who don't know, we do Stream Raiders on this stream. We're just going to do it we just do it on the side. I'm starting a battle right now. There we go. So if you want to fight in Stream Raiders, just type !battle in the chat, thusly, and click on that link, log in with your Twitch credentials, and you can play with us. Easy, easy, easy. All right, here we go. Let's get into it, chat. Here we go. Here we go. Here we go. PowerPoint slides, I know. Again, Dan's game. Okay, get it out of your systems if you need. Get them out of your systems. We're going to go into, we're going to start, we're going to learn a little bit. What are we going to learn today? What are we going to learn? Alright, I gotta get my there we go. Alright, who am I? Those of you who are new to the stream, welcome! Thank you so much for coming in. Thank you so much. I hope I can teach you stuff today. Who am I? I'm a career cybersecurity professional. I've been a forensic analyst, a threat hunter, a software engineer, and I'm a pen tester. I'm a professional pen tester, red teamer for are the slides going to be available? Yeah, I will make the slides available. I'm pen tester and red teamer for a consulting firm. More recently, I've been doing Twitch streaming. I am the owner, lead admin of the InfoSec Prep. Oh my goodness, Susvarus? How many even? 10 subs? You madman. You people, Susvarus and Nightmare are completely out of control. These people cannot be helped. Kelpmap, thank you for the follow, my friend. Cthulhu Fatagan. So I'm in the United States. I was the creator of the InfoSec Prep Discord way back when I was doing OSCP. Brief history of myself there. There's my links if you want to join, if you want to follow my Twitter or whatever. Easy enough to find me. Alright, moving on. No one cares about who I am. We care about what I bring to you. We care about the information that I bring. Okay, Cat, Mr. Rootbot, thank you so much for the follow, my friend. Cthulhu Fatagan to all of you. Wow, Naga as well. Thank you so much, Cthulhu Fatagan. Stop distracting him with all this stuff. Yes, stop giving me money. No, I do my best to be interactive, but I do have to get to what we're going to talk to. So what agenda? What are we talking about? What are we going to talk about? First, we're going to talk about the CPU architecture. What the CPU does, how basically it does it. Really high-level stuff. If you don't know anything, we're going to start from nothing. We're starting from nothing, I promise. Slytherin Tupac, you psychopath. You're another sub. x86 assembly primer. We're going to start talking about x86 assembly, just really basic. Again, you don't need to know any programming for what I'm going to teach you today. And then we're going to talk about Win32 process memory, how it's laid out, with a focus on the stack. Okay, a focus on the stack. And then we're going to talk specifically about buffer overflows. What do we mean when we talk about buffer overflows, okay? What do we mean when we talk about buffer overflows? And then we're going to do the demo. We're going to get into the dark magics, and I am going to demonstrate the madness of binary exploitation to you. It truly is crazy, my friends. I'm super excited to get to it. Let's get in. So, what does the lab setup look like today? For those of you who are in my Discord, I sent out a really quick way of setting up a quick lab that will allow you to follow along with the stream. You're gonna need Windows XP Service Pack 3. Data execution protection should be set to always off. It shouldn't be necessary, okay? It shouldn't be on anyways. Immunity debug, you're gonna need immunity debugger, preferably with Mona, though you don't really need Mona. And then War-FTP, version 1.65. This is a real-world FTP server, with a real buffer overflow that was discovered, I think 20 years ago. It's a little old, but it's still valuable as a teaching, for teaching. 0x Kane, Pinkman Jr., Chai 9654, and Nix Rocks. Thank you so much for the follows, my friend. Good to have you here, Cthulhu Fatagan. To you. All right, and your attacker machine should just be Kali Linux. I'm going to be using a 64-bit one. It doesn't matter what architecture your Kali Linux machine is. Make that a little bit smaller. There we go. All right, back to it. All right, the CPU. We're jumping into it. We're getting into it right off the bat. The CPU. So here's the basic outline of what your computer looks like, okay? A high-level overview of what the computer you're on looks like. It's just, again, it's oversimplified, okay? But you got the CPU, you got your input-output devices like your hard drive, your keyboard, your mouse, all that stuff. And then you got your memory, your RAM. That's your RAM, and those are all connected by the system bus, on the motherboard. The motherboard has the system bus on it. All right, CPU. All right, so real basically, here's what your CPU looks like. Okay, is your username in relation to the package manager and so? Oh yeah, okay. It wasn't talking to me. I thought you were asking me a question. So this control unit's basically the brain of the CPU. Okay, it gets instructions from the it parses them, and then it gives the execution unit things to do, and it also retrieves and stores things from memory. The execution unit is what's actually the body of it. It's what's actually doing the executing. Hence execution unit, and it uses CPU registers and the flags to do that. Now, what are registers? We're going to be talking a lot about registers today, boys. Very important to talk about registers. Okay, so what are CPU registers? They're little bits of memory inside of the CPU that the CPU uses for the actual instructions, the actual mathematical operations it's doing, moving things around in memory and that sort of thing. It uses the registers for that. You would ask, well, I have 32 gigs of memory in my computer. Why can't it use just some of that memory? Well, the answer is the registers can be accessed much more quickly, my friends. Orders of magnitude more quickly. And so the CPU has its own really fast memory to do its calculations on. So it's very important that you understand what registers are. We're going to be talking about them all day long. All day long we're going to be talking about registers. And the flags are used to flag certain things. They're used to indicate certain states and events that occur as execution is going on. Like if you're in a loop, a certain flag is set that indicates that the loop is going to continue for another revolution and things like that. All right, what's next? Continuing. So again, we're going to go deeper into the 32-bit registers. The CPU registers, small bits of, so I already explained this. You have many different kinds of registers. The ones we're most concerned about are these general purpose registers right here. We're most concerned about these. The floating point registers deal with floating point operations, as they could indicate, and we may actually see a floating point operation later on today. I will point it out when we get there. The segment registers are for these are mostly for legacy. These are from the days when These are from the days when memory was organized by memory, when there was like when your computer's memory was organized through a method called memory segmentation. Now it's done through paging. So these registers are mostly in there just for legacy. Then the MMX and XMM registers, also similarly for legacy. The XMM registers are still used sometimes, but the MMX are used rarely. But you can still make use of these registers and the MMX instructions for exploitation. They often are. They're not used for regular things, but you can make use of them as a hacker for sure. And then you've got flags, and you have this little puppy right here. You have this little rascal, EIP. EIP. We're going to be talking about EIP, boys. We're going to get into EIP. Safe Amis, it's okay. We're just trying to establish a baseline of understanding. I don't intend for you to walk away from this computer science professionals and CPU architecture, okay? But this little puppy, all you really need to know from here is we're going to be focusing on the general purpose registers, and we're focused on EIP. Yeah, that stands for extremely important pointer. It's not what it stands for, but believe me, EIP, we're gonna have a special slide just for EIP later, okay? Don't jump ahead. Don't jump ahead. We're gonna get there. We're gonna get there. And RIP Ong31D. What are these lunatic words that you bring into my chat? RIP does not exist, and don't you try to convince me that it does until we have time to cover 64-bit buffer overflows. Okay? But for right now, we're focusing on 32-bit. We live in a 32-bit world today, my boys, and I'm going to explain why we're going to do 32-bit here in a minute. So these are your general purpose registers. As indicated, these registers are general purpose registers. You can use them for anything. The CPU has certain operations that need to be performed in certain registers, like EAX right here. The EAX register, 32-bit register, okay? It is 32 bits, or in other words, or 4 bytes, okay, to this register. And you can subdivide it. If you refer to AX instead of EAX, you're referring to just half of the first half of EAX can be subdivided into AX, and then the first byte of each of AX can be divided into AH and A high and A low. Really not important for you to learn about that. This is only important when you're trying to do your own custom shell coding and stuff. We're not going to do anything like that. I'm just pointing out, again, we're establishing a baseline of understanding, okay? These are your general purpose registers. EAX is generally used for mathematical operations. Some mathematical operations must use EAX actually, but in general terms, these registers can be used for just about everything. Like just about anything. You can use them for anything you want. As far as exploiting a system is concerned, you can use them for anything. And then we have the other general purpose registers. Looks like I formatted this slide slightly differently. But you have ESP and EBP. These are the stack pointer and the base pointer. We're going to talk about these later, boys, when we get into the stack. Mario MPH182, thank you for the subscription, my friend, the Prime subscription. Welcome to the Alhaz Red team, my friend. And the base pointer is another. We're going to talk about these when we get to the stack. ESP and EBP are your stack frame defining registers. They point to wherever in memory the stack is right now. And then ESI and EDI are source index and destination index. This is used for string operations. Like if you're moving a string around in memory, ESI and EDI would be used. But again, all of these registers can be used for just about anything. The ESP and EBP are used to define the stack, but that doesn't mean you can't use them for stuff. It just means you need to be cognizant. You can't use them for your shell coding and stuff, but you need to be cognizant of what these registers mean to the CPU so that you don't break anything. They're tiny bits of RAM. Calling them variables isn't really accurate. They're not variables. Like I said, they're tiny bits of RAM inside of the CPU itself. They hold values for a short time. They do. You can think of them like variables at a really high level, honestly. It's not going to hurt anything if you think of them like that. They're just little bits of RAM used for CPU operations. Okay? And if you have questions, feel free to ask questions. I'm here. I am here to help you and teach you guys, okay? And these are so these are the common functions: accumulator register, base register, pointer to data. Basically all of these are pointers to data. All of them are pointers to data. The ECX is used specifically for loops. It'll count if you're going through a loop a certain number of times. ECX will have the number of times that you're going through the loop in it. Can I turn it down? Sure. Turn down the background sound. Hopefully that's a little bit better, Nix Rocks. The Joker Original, thank you so much for the follow, my friend. Cthulhu Fatagan, good to have you here. Alright, next one. ESI, EDI, the source index and data destination index used for string and memory operations. ESP and EBP stack operations. E-flags, we're only going to glance at this slide. This is only going to confuse you. There's a separate register called E-flags. It's also 32 bits. And it's used for the various bits being flipped, or it kind of indicates various things, like carry flags are used for carry operations in arithmetic. You don't need to know this. We're not gonna focus on flags today. Oh boy, here we go. Here we go. EIP. Extremely important pointer. The instruction pointer. What is EIP? What is this lunacy? This mad, this cosmic lunacy that we're viewing. EIP contains the memory address of the next instruction to be executed. EIP essentially contains an anchor for the CPU. It tells the CPU where to go next. When you're done executing your current instruction, go to the address in EIP and continue execution. For this reason, since it controls execution of the CPU, EIP is the focus of exploitation. Just about every bit of exploitation you can come up with, like even like higher level stuff like web exploitation and stuff, fundamentally it's about controlling this. It's about controlling EIP, where the CPU is going to execute. So, because control of EIP, if you can put arbitrary values in EIP, you can control what the CPU executes next, which allows you essentially control of the computer, for all intents and purposes. It allows you control of the computer. Most RCE exploits consist of creative ways to place arbitrary values into EIP. That's what we're going to be doing today. I want you to focus your minds around that fact. We want to control EIP and send it to a place where we control, and to give it instructions to execute on our behalf. Is everyone following me on that? Does everyone understand the importance of EIP? It is crucial that we because we're going to be talking about EIP an awful lot today. So you may ask, why don't we just write directly to EIP? Why don't we just have like an assembly instruction? We're going to go into assembly here in a second. Why don't we just have an assembly instruction that writes directly to EIP? EIP is read-only. Like it says on this slide, EIP is read-only. So you can only control it indirectly. And we're going to talk about some ways to control it indirectly here in just a little bit. Maz7 Alib, thank you so much for the follow, my friend. Maz Talib, I guess. I guess that's supposed to be a T. Maz Talib, thank you so much for the follow, my friend. Cthulhu Fatagan, good to have you here. Coming back, yep, saw it in high school, yep. Stack lives in RAM. The stack does live in RAM, yes. The stack lives in RAM. We're going to talk about the stack in just a little bit. Don't jump ahead on me. We're going to get to the stack. Today's all about the stack. We're going to be talking about the stack all fucking day. All right, assembly. Now we're going to talk about what assembly is. And you don't need to know any programming for this. It's okay. You don't need to know any programming. This is really baseline level, so that we can talk about what we're going to talk about in the demo. All right. So what is assembly? I know the boomer meme. Look, it's funny to me. Okay. I'm basically a boomer. I find this funny. Okay. Low-level programming language. So it's an extremely low-level programming language. It's basically as close as you can get to ones and zeros without actually being ones and zeros. I'm wondering what the point of a buffer overflow is just to make a computer crash and take down a system? That's what we're going to get to, Paranoid. Some buffer overflows are not exploitable, and they're just used for denial of service. But we're going to talk about ones, but not all of them. In fact, a good sizable proportion of them allow you to gain control of the system and execute code. This is that's what we're going to talk about today. I'm going to use a buffer overflow not to make a computer crash. I'm going to use it to make it give me a reverse shell, to make it connect back to me and let me execute and open a command prompt for me. Is this rewatchable after the fact if I'm not subbed? Yes, I have my videos open to everybody. You can watch it after the fact. So it's assembly. The assembly comes in basic variants that are in different variants depending on the kind of processor you're using: Intel, ARM, MIPS, etc. Most of the time we're going to be dealing with the Intel syntax, and we're going to talk about here in a second. and there's almost a one-to-one correspondence with machine language. And we're gonna get into what. Okay, so Johnny Sioka, thank you so much for the follow, my friend Cthulhu Fatagan. So the reason that programming languages even exist, okay? The reason that programming languages even exist, Mupple12, thank you for the follow, Cthulhu Fatagan, is because there's a language mismatch between what human beings speak and understand and what computers speak and understand. This CPU can only understand ones and zeros. Only understands ones and zeros. But we don't understand ones and zeros. Ones and zeros are a pain in the ass to read. So we invented programming languages as a way of converting instructions from human readable syntax to machine language instructions so they can be executed by a CPU. Okay? And every single... I feel like following and refollowing just to hear the Cthulhu part. Hey, I'm going to say it like 5,000 more times today. I say it. We are devout followers, crazed hacking cultists of the old gods of hacking, okay? We serve them by doing our daily devotions with CTFs and buffer overflows and whatever comes to our mind. What is this Cthulhu Fatagan thing? It's a Lovecraft thing. It's an HP. It's a reference to the writings of H.P. Lovecraft. All right. So what assembly is essentially those ones and zeros put into words, really simply. Okay, so here's an example of assembly language. You would read this: move EAX EBX, XOR EAX EAX, add EAX at 0xFF, and then you use an assembler and a linker as a translator. What you basically compile it to convert it to machine language instructions. Okay. So that's basically what assembly is. That is the Intel syntax it is. We're going to be doing only Intel syntax today. AT&T syntax is disgusting. It's gross. It's absolutely revolting. How did you get a pic of me? Yeah, exactly. So where is assembly used? Broad applications in all fields of computing. If people write in assembly not only for shellcoding, they write for like really hardcore optimization. Can you code malware in assembly? You absolutely can. In fact, and I'm going to show you how to do a little bit of that today. You absolutely can code malware in assembly. It's called shellcode in assembly, but you absolutely can. Okay? So, Muppy12, thank you for the follow, my friend. Cthulhu Fatagan. So it's also used by developers for legitimate purposes to do like really hardcore optimization. If you want your software to scream along and be as efficient as possible and run as quickly as possible, you need to work in those low-level languages, assembly, C, that kind of thing. That gives you the tightest control over the CPU architecture. It doesn't really get any tighter than assembly without going straight into ones and zeros. InfoSec uses. Why do we care about assembly? Maverick, thank you so much for the follow, my friend. Cthulhu Fatagan. What do we have? What use do we have for it? It's good for shellcoding, for encoders, memory manipulation, and execution hijacking and exploitation. Okay, so that's what we're going to use it for today, my boys. Why is assembly? I don't know why. When I was making the presentation, I just felt like making it this scene from the Avengers kept popping into my head. So now you guys can just stare at that. Assembly is a gateway to understanding memory, processor exploitation, reverse engineering, shellcoding, all of the dark, deep magics, okay? The non-Euclidean geometry from real, it's all written in assembly, okay? It's all written in assembly. This is the language of the old gods themselves, okay? Without a grasp of assembly, it is impossible to master any of these fields. This is going to be a very brief introduction, my boys. Very, very brief introduction. This is not intended to make you a master assembly coder. Just to introduce you to some basic instructions that we're going to be using today. Okay? Intel architecture. Okay, so this is the difference between x86 and x30 and from between 32-bit and 64-bit. If you ever wondered what the difference is between a 32-bit system and a 64-bit system, the difference is basically just the register size. That's it. 64-bit processors, as their name indicates, have 64-bit registers, and the registers are different. They're named something different and things like that. But it's crucial to know, it's crucial to understand, and x86 only has 32-bit CPU registers. Why does this help to have bigger registers? Because you can deal with larger amounts of memory this way, okay? With x86, you can only deal with about 4 gigs of RAM. With 4 gigs of RAM before you're exceeding the boundaries of what your CPU can actually efficiently manage, okay? So 64-bit came about as necessarily because we started having computers that wanted more RAM. That's about it. But keep in mind that 64-bit x86 is just an extension of 32-bit. All the instructions are the same, basically. The instructions are all the same. The registers are named something different, but they all have similar functions. Like, it's all just an extension, so moving from 32-bit to 64-bit is very easy. There's also, I don't even know, like, is this 17 million? Oh, no, 17 billion. Over 17 billion gigabytes of RAM are possible in a system with a 64-bit CPU. I'm as PC master race as they get, but I'm not looking to upgrade to 17 billion gigabytes of RAM anytime soon. Gotta go to bed and get up in 7. Mojo Dojo 101, thank you so much for being here, my friend. You have a good evening. Come back and watch the VOD. We've got some great stuff coming up. And I'm gonna give you, I'll definitely supply the presentation as well. Alright, why bother with 32-bit? You might ask, Al, what the fuck? Why are we bothering with 32-bit, okay? Why the fuck are we taking our time to learn 32-bit? Because every machine I know of is 64-bit. My machine's 64-bit, my friend's machine's 64-bit. Those are all the computers I'm aware exists. Like, that's, and the answer, the short, there are several answers to that question. First of all, almost all 64-bit machines that are currently out there, except for a couple of operating systems like Mac OS, almost all machines, Windows included, the vast majority of the market share still runs 32-bit for legacy purposes. And also, even now today in 2020, I would say probably the majority of machines that are still on the internet out there are 32-bit machines. There is a staggering amount of hardware out there that is still 32-bit. And even the machines that are 64-bit, they run 32-bit. They run 32-bit processes just fine for legacy purposes. Okay? For legacy... Safe Amas, you absolutely should go to sleep. But thank you so much for being here. It's good to have you. But also, you basically need to... We're going to crawl, we're going to walk, and then we're going to run. Later on in this stream, not this stream in particular, but later on in future streams that I do, we're going to cover plenty of 64-bit stuff, okay? We're going to talk about all kinds of 64-bit... 64-bit buffer overflows. But today we're starting out with the simplest stuff, and the stuff that you're going to see on OSCP. On OSCP, you're going to see 32-bit, and again, there are a lot of processes that are only 32-bit that are running on 64-bit systems. 64-bit systems can still run 32-bit code in most cases. Highly Anog, thank you so much for the follow, my friend. Cthulhu Fatagan to you. Oh, I think I missed Laruku22TW as well. Thank you so much. Cthulhu Fatagan to you. Alright, there you go. Is 32-bit that often? Yes, absolutely. I see 32-bit processes all the time. Your Windows machines, a lot of the processes you're probably running on your machine right now are actually 32-bit processes, and you just don't even know it. A lot of software is that way still. Is still in 32-bit. So it is far from gone. I would say it's outmoded, as in, like, we're moving into 64-bit, but 64-bit is far from being mandated. Alright, instruction format. Here's basically what an assembly instruction looks like. Okay? Here's basically what an assembly instruction looks like. First, it's going to start off with a label. We're not really going to worry about the labels today. Those are optional. The mnemonic, that's going to be your push, your add, your XOR. Down here in this example down here at the bottom, this add is the mnemonic. And then the operands, like whatever registers you're working with. And then you can also add a semicolon and a comment after. And the comment works like a comment in any other programming language. The comment is ignored. It's just a note. It's a developer note, basically. Essentially, add EAX EBX. Now, you want to note that this is the Intel format. So the ordering of the registers is destination and then source. So when you say add EAX EBX, we're adding what is in the EAX register to what's in the EBX register, and then storing it in the EAX register. Okay? Does that make sense? I've I've made a little example over here of what this actually means, okay? EAX, this instruction right here means that whatever's in the EAX register is equal to what's in there right now plus whatever is in EBX. Does that make sense? Will I provide the slides? Absolutely, I will provide the slides. Absolutely, I will. Will it be recorded? It's being recorded on Twitch right now. You're going to be able to watch all of this. Not a problem. A mnemonic is not required if the line contains only a label or comment, blah, 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 blah. Okay, doesn't matter. But basically, this is the basic structure of an assembly program, of an assembly instruction, okay? And now we've already hinted at the different syntaxes. There's basically two different kinds of syntax for assembly language. There's a good kind and a bad kind. There's the Intel syntax. It looks like I spelled it wrong here. Intex syntax. Intel syntax, as you can see, is much cleaner. But AT&T syntax, the biggest changes are these dollar signs that indicate constants versus registers. These dollar signs and percent signs. And also they go, their registers are their operands are listed source to destination. So source first and then destination. Intel is destination and then source. That's the key thing to understand. That in the Intel syntax, the destination register is the first thing. And that the source is the second thing. And it's the other way around for AT&T. Hiwu, thank you so much. You have the Cthulhu Photogin, my friend. Thanks so much for being here. All right. So here's an example function. I know. It's like looking at an Elder Scroll. I get it. Okay. You're like, what the fuck? This is way too much. What is even happening here? What madness has occurred? You're reading a page of the Necronomicon. Okay. This is the language of Yog Sothoth himself. Okay. This is the reality warping language. Okay. You don't need to understand what we're going to actually go through this later. I'm going to go through exactly what this is doing. This is a very simple function. This is an example of a very simple function in assembly. Okay. And I'm going to go through everything that this is doing. Everything, yeah, exactly. I'm going to go through everything this is doing later on. We're going to come back to it after we talk about the stack, okay? So, that's all for that's the introduction to assembly. Again, you're not a master of assembly now. I get that. And Hosh, thank you for the follow, by the way. Cthulhu Photogin. And the Shaughnessy, thank you so much for the follow as well, my friend. Cthulhu Photogin to you. We're talking about the stack. Now we got to talk about the stack. So, when an application is initialized, Windows creates the process and assigns virtual memory to it. So you have a page of memory or more that's dedicated to that process. And 32-bit processes of addresses ranging from 0 to FFFFFF in bits. This is all the bits set in the register. The lower half are used for kernel user mode, and the upper half are used for kernel mode. Yeah, so, and Windows uses the flat memory model, which is not going to come into play today, but it could come into play for other exploitation. All right, here's what process memory looks like, okay? This is basically what it looks like. Notice that down here at the bottom, you have kernel memory. That memory is reserved for the kernel. We're not concerned about that, okay? All the rest of this, you have DLLs that are loaded. You got the data block of the main thread that are loaded here. We're mostly concerned about the stack and the heap. Okay, the stack and the heap we're going to talk about only very briefly today. The stack is the focus of the stack is the focus today. Okay, what you should understand from this picture in particular is that as the stack grows from higher memory addresses to lower memory addresses. So it grows down. As it gets bigger, it goes to lower memory addresses. The heap is the other way around. They basically grow away from each other. They start at the same address, and they grow away from each other. These are two memory structures that are used for two different things. So that's basically what I wanted you to take from that. We're going to go back closer into it. We're going to go further into it here in just really, really shortly. Smallest Monkey, thank you for the follow, my friend. Cthulhu Photogin. Alright. Did I? Okay. Alright, we'll talk about what the stack actually is. The stack is the place in memory where function like temporary ephemeral variables like function parameters and variables that are declared and set in functions and things like that. The stack is the place where those are stored, okay? The stack is the place, so if you, for example, had I don't know why I would say this, I'm just going to pull this fucking, I'm going to pull this fucking example just completely out of nowhere. Say you had a program that accepted a username as you were logging in, and the user submitted a username. That username is then stored on the stack to be used by the program later on. Okay? And whenever a new function is started, whenever you call a new function in your program, a new stack frame is created. Like parameters are pushed onto the stack and things like this, and a return address is pushed onto the stack that indicates where execution will go next. Once that a return address, every time a new function is called, this is crucial to understand. Listen up. Listen, look at me, okay? Whenever a new function is called, the program creates a new stack frame, and at the bottom of that stack frame, or close to the bottom of it, is going to be a return address. That address tells the CPU where to execute, where to go next once it's done executing that function. Okay? This is very crucial that you understand this. I'm going to say it again. The return address, whenever you call a new function, the return address, let's do a quick notepad stream. Let's just do a quick notepad stream so I can point it out. So let's say, quick notepad stream. Okay, so let's say you've got your main function. So you got int main, and you've got string do something, str. It's accepting an argument of str. This is in Python, because I'm most familiar with Python. Okay, so when program execution starts, it's going to go to int main. Okay, so the main function is where the program is as the name indicates, the main function of the program. Okay, so, and let's say all int main does is call do something. Let's say it sets str equals Cthulhu Fatagan. Okay? And then it's going to call the do something function with that string as a parameter. Okay? Very, very simple stuff. Okay? When the process starts, it's going to create a stack frame for main. Okay? Then it's going to set a string to Cthulhu Fatagan. It's going to store that string on the stack, in the stack frame for main. Okay? Then it's going to call a new function. The CPU is going to go, okay, I need to go somewhere else, to some different place in memory to find this function to execute. And stuff.stuff. And I guess str. And return. Stuff equals stuff, return stuff. Whatever. It doesn't really matter, okay? So the CPU is going to go to a different place in memory, and in order to save its place and know where to go once it is done executing, because again, this is located in a different place in memory from this, okay? The CPU, when it reads this, is going to say, okay, I have to go find this function in memory and execute it. So it's going to go to this spot in memory, it's going to create a stack frame for this function, and it's going to execute this function, storing things on the stack and moving stuff around. And before it actually starts executing stuff in this function, it's going to store the return address of where it should go. Let's say it's do something. Let's say continue. Let's say that there's an instruction, program.continue, I guess. When this function is called, it's going to place the address of this instruction onto the stack, it's called a return address. This is placed onto the stack, and a new stack frame is created for this. Okay? This is absolutely crucial. That's why I'm focusing on it. So, let's say, we're going to go over what can go wrong here. But after it's done executing this function, after the function returns, the CPU is going to say, okay, what was in my return address? And it's going to go back to that place on the stack where the return address was stored, and it's going to come right back here, and with the next program line, it can continue execution. Is everyone following this? Is everyone with me? If you're not with me, ask questions. Ask right now. I really want you to ask, because this is absolutely crucial that you understand this flow, that you understand what is happening here. That the CPU needs to save its place before it goes to another spot in memory to execute. Okay? How are you? First time in this channel? Kachalimbu, thank you so much for joining us, my friend. It's good to have you here. I generally do CTFs. Today, we're doing a very special day. Good day. You picked a good day to be here, man. You picked a good fucking day to be here. You haven't missed anything yet. You just missed some boring PowerPoint slides. We're going to be doing a full buffer overflow manual exploitation here in a little bit. Can you run through that just one more time? Yes, okay. Go real slow, real slow. I know this is annoying, but I have to make sure that you understand this, okay? So when the program starts, when the CPU starts executing the program, it's going to go to the main function. The main function is the main function of execution, okay? That needs to be parentheses. Okay. It's going to create a stack frame for main. It's going to set a string to Cthulhu Fhtagn, and it's going to store that string on the stack inside of main stack frame, okay? Then it's going to hit this function, and this is a function call to this function. So the CPU has to go somewhere else in memory to execute this. Okay, so it's going to save its place so it knows where to come back, and it's going to put this on the stack. It's going to push the address of this instruction onto the stack so it can come back to it later and continue execution. So it's going to go into string do something, and then it's going to do some stuff. It's going to create a stack frame for do something. It's going to do some stuff, and then after it returns, after it finishes executing this, it's going to go back to its return address, the place that it saved, its saved place, and it's going to say, okay, I've got my saved place has come back here, continue execution, and it's just going to merrily continue on executing after that. Does that make more sense, Paranoid Violence? You following me? Are you going to make use of... I absolutely will. I'm going to make use of breakpoints. I will absolutely be using breakpoints. You're going to see every step as it happens. Okay, cool. All right. So we can move on. The heap is used for other things. It's used for large blocks and blobs of memory, dynamic memory allocation. The heap has its own set of exploits devoted to it, but that's a discussion for another day, okay? That's a discussion for a future time, okay? But today we're all about the stack. We're really concerned about the stack. The schedule doesn't show anything. Is that normal? Maybe I deleted it. I'm very, very busy, so I've been fluctuating a lot on what days I'm actually streaming. The best way to know when I'm streaming is to follow me on Twitter, because I tweet every time, a few hours before I'm going to stream. I really need to settle on a schedule though. All right. So assembly, which we just talked about, has several instructions that interact directly with the stack. The most important of these are push. Oh fuck. Push, pop, and ret. Okay. Push decrements ESP. Now keep in mind the stack grows down. The stack grows down. It grows to lower memory addresses. So when ESP, the stack pointer, which points to the top of the stack, it points to the lowest memory address of the stack. My eyes are itching. I gotta go to sleep. Definitely watch the VOD. Hey, Safe Amos, thank you so much, Cthulhu Fhtagn. You have a good night, man. The VOD's gonna be up. I'll produce the slides. You're gonna be able to do everything. Thank you so much for being here. I love it. I love having you all here. This is great. So, ESP points to the bottom, the lowest memory address of the stack, the top of the stack. Remember, the highest point in the stack is at the lowest address in memory. So if you decrement ESP, you are increasing the stack size because it grows down. It's gonna place the operand onto the top of the stack. So push EAX will place the contents of the EAX register, the EAX CPU register, onto the top of the stack. Okay? It's gonna decrement ESP by 4 bytes, by 32 bits or 4 bytes, and it will put the value in the EAX register on top of the stack. The stack is it's why it's called a stack. Think about it like a stack of plates, like in a restaurant, a stack of plates. You put a plate on top of the stack, and then the first plate to come off is the one on the top. It's a last in, first off data structure. Okay? So that now POP-EAX does the opposite. It adds first of all, it takes the value, the 4 bits from the 4 bytes, excuse me, the 4 bytes from the top of the stack and puts it into EAX, and then it increments ESP, means like the stack shrinks. Is everyone following this? I know it's a little bit confusing because the stack grows down, but hopefully that this makes sense. And then RET. I gotta wake up early tomorrow. Good night. Yeah, thank you so much for being here, Dragon. It's great to have you here. Can you repeat it? Can you repeat it again? Yes. Okay. So, push EAX. When a push EAX is executed, first it's going to decrement ESP, meaning the stack is going to grow down. It's 4 bytes. 4 bytes. 32 bits is 4 bytes. Because 8 bits per byte. There are 8 bits in a byte. 32 bits means 4 bytes. It'll make more sense when we actually get into the coding. It's gonna decrement ESP, increase the size of the stack by 4 bytes, and then it's gonna put the 4 bytes that are in EAX on the top of the stack. That's all push does. Pop does the opposite. It takes 4 bytes off of the top of the stack and puts them into the EAX register, and then it increments ESP, so the ESP always points to the bottom of the stack. It's 32-bit architecture. 32-bit means it operates mostly in increments of 32 bits, 32-bit registers. And RET, as its name indicates, transfers program control to a return address located on the top of the stack. This is what the program is executing when it is returning. When I showed back into the Notepad stream, when it returns, it is executing a RET. RET takes the 4 bytes from the top of the stack, the top 4 bytes on the stack, and puts it into EIP, the instruction pointer, the one we want control of. Okay? The instruction pointer, and then it goes there to execute. Is everyone following? Is everyone following? All 3 of these instructions are going to be really important today, guys. Real important. RET, it's placed on the typically when a call instruction is placed, like when this function is called, when this function is being called, a call instruction in assembly is executed, and then a return address is placed on the stack, and RET is the opposite. RET undoes the call and returns execution back to where the program left off before it called. That's what RET does. Is everyone following? Okay. When will you start the buffer overflow? Pretty soon. We're getting close. It's close to the end of the slides here. Here's the example function. We're gonna push. So this first part is the function prologue. The first thing it's doing is it's just adjusting the stack pointers to make space on the stack to make a new stack frame to operate in, and then it is taking some values that are in EAX and EBP, which are function parameters. These are function parameters, and it is loading them onto the stack. It is putting them onto the stack, and then it executes a call. And that call is for a string copy function in C. Very, very simple. This is a very simple function. I know it looks like this is like the ancient Sumerian text. Okay? This is like the ancient Sumerian texts. Okay? This is like but focus, like this part is the function prologue. The first 3 lines are basically the function prologue, where the program is just making a new area on the stack. It's increasing the stack size and making space for this new function. Then it's going to push parameters onto the stack. In 32-bit architecture, function parameters are put on the stack. That's not the case in 64-bit, but we'll talk about that at another time. Okay. And then it's executing a call. After the parameters are set up, it's going to call. And it executes the string copy function. Then it comes back and it returns. Like, really, really simple. All right, here's the stack. Again, we've talked about grows from high addresses to low addresses. So here's ESP. ESP sits at the top of the stack. Is OSCP going to be x86? Yes, GUI Senpai, it is. ESP is on the top of the stack. All right. And then EBP is the bottom of the current stack frame, like the current function stack frame. That's what EBP is. And then EIP is saved right after EBP. Right after the current stack frame, there's your return address. That's where the function knows to return to. Okay? And then there's the function arguments. Okay? Really, really simple stuff. Grows from higher to lower addresses. Yes. Okay? The stack. Every time a function is called, the function parameters and the saved values of the stack as well as EIP. When the function returns the saved value of EIP, so every time a new function is called, the program needs to save its execution state so it can come back and continue executing after that function is done. So when the function returns the saved value of EIP, the return address, as it's called, is popped off of the stack and returned to EIP so the application can continue execution. Everyone's with me so far? You can ask questions. This is what we're talking about. Is this happening within the CPU, right? It's happening within the CPU and memory. It's the CPU interacting with memory. This is in your RAM. The stack is in your RAM. But the CPU is what's actually executing the instructions, obviously. All right. Memory, you mean RAM. Yes, I mean RAM. By memory, I mean RAM. Okay. Why does all this matter? Why does this matter? Why? Because I'm just trying to torture you? I'm just trying to teach you this really fucking dull shit? No. It matters because we can exploit it, chat. Okay, so here's what we're going to do, all right? Some lower-level programming languages, C and C++ most primarily, do not check to see how large data is before it puts it onto the stack, okay? So, if user-controlled input is accepted in one of those fields and is placed into a variable that is located on the stack, the program is not going to check if the variable on the stack, if the amount of space it's allocated on the stack for that variable is large enough to accept the amount of data that is coming into the program. Does that make sense? Is everyone following me so far? Is everyone following me? And we're going to walk through this code so far, okay? It does not check. And for that reason, if you send... that matters a lot, okay? So let's say this is a very simple code snippet. This is in C, okay? Very simple. So first it's creating a char buffer A 50. This is a string. It's creating a string. This is how strings in C work. They're arrays. They are arrays of characters, okay? It's creating a buffer A of 50 characters and a buffer B of 16 characters. Then it asks the user, it prints to the screen, what is your name? And then it gets buffer A is getting input from the user. So the user types in their name, and that is placed into buffer A. And then an strcopy function, string copy function, is executed to move the value that's in buffer A into buffer B. Do you see what the problem might be? Are you guys seeing what the problem might be? Buffer A has 50 characters it can accept. So let's say a person, well, actually, technically it can accept 49 characters, but we won't go into why that is for a little bit yet. We'll go into why that is a little bit later, but it can only accept 49 characters because the last one needs to be a null byte. So let's say a user puts in a 40-character string of their name. They have a really long name. Their name is like Narlathotep or Shub-Niggurath or something like that. Okay. And then that gets loaded into string copy, buffer B. Again, string copy is not going to check. It's just going to happily start copying data from buffer A to buffer B. And because of that, you can overwrite portions of the stack. The stack will be overwritten, saved those values that were on the stack. All of this space for my var, all of this down here is going to start getting overwritten, little by little. Does that make sense? Is everyone following me? This is crucial. Okay, this is crucial to understand. This is what is referred to as a buffer overflow. Okay? So if you're coding in like a scripting language like Python and stuff like that, those languages are going to check. But the low-level languages, C, C++, assembly, they don't check. The developer needs to have code in there to check the size of the variables. All right. Buffer overflow. If boundary checking is not done, too much data will be written onto the stack to fit the bytes that are allocated for it. The excess data will overwrite higher memory addresses sequentially, and everything stored there, perhaps even beyond the current stack frame. If the stack is used to store memory... This is the crucial part, okay? The stack is used to store memory addresses to be loaded into EIP at some later time. Okay, remember we said that the program stores the return address of where it wants to come after it's done with that function. It stores that on the stack. Right here, saved EIP. If that is overwritten, you can place an arbitrary value here, And you can send the program anywhere you want it to go to execute. You can have it execute arbitrary instructions on your behalf. Are you following me? Is everyone following is everyone follow what this image is trying to show them? So we wrote a bunch of A's into this variable that was too big for the variable, and it overwrote saved EBP, it overwrote saved EIP, the program, and it's gonna with all these A's, the program's just gonna crash. A's are not an executable address, okay? But if you put a memory address here, it will execute it. Okay, it will go to that address and it will execute. That is what we are going to be doing, and I'm going to show it to you guys. I am going to show it to you, like in extreme detail. I'm going to show you everything. Okay, and here it is. Here it is again. String is overwritten. What results is control over EIP itself, and therefore the ability to hijack the execution flow. Okay. Another visualization. Okay, here's unallocated stack space here, and let's say you're writing a hello into this. This is a stack space of 12 characters. There's enough space for 12 characters. The person and it accepts input of hello, and then it terminates it with a null byte. Really easily. Hello with a null byte at the end fits within 12 characters. No problems. Okay, doesn't cause any issues. But if the user puts in a whole bunch of goddamn A's and then a memory address, in like exactly where, again, you have to figure out where the memory address is being overwritten. But if you figure out where the memory address is going to be overwritten, which I'm going to show you how to do later, you can put an arbitrary address here and it will just jump to that spot in memory and execute. Okay? We need to know the size of the buffer so we can put more into it. Yes. Felix, can you rewatch this later? Absolutely you can. It will be up on my channel. Just watch the VOD. All right? I think we've gotten there. So, other possibilities. The return address is only one of only one of several ways in which the stack could be exploited to gain control over EIP. Lots of memory addresses are stored on the stack, and any of them that are intended to take the CPU somewhere to execute can potentially be exploited. We may be talking about more of those later. Other more, yeah, okay, there you go. Other more, yeah, there you go. Defense mechanisms. We're not going to worry about any of these today. We're going to be exploiting a Windows XP system. Windows XP doesn't have ASLR, doesn't have data execution protection, it doesn't have stack canaries. These days, if you were going to try and exploit a buffer overflow, you'd have to contend with some or all of these instructions. They all have bypasses. They all have ways you can get past them, but they definitely complicate the execution. What we're going to look for today is a really simple one, so that Ang31D, do not introduce these lunatic, these mad words into my chat, okay? Don't even, okay? No, stop Googling. It's just gonna confuse you. Actually, we may be using a ROP chain later, but we'll get to that when we get to it. Okay. How about ffuff? Let's use ffuff. Each of these, again, we're going to cover these. We're going to cover the bypasses for these later on in future streams. Not today, okay? But these are the defense mechanisms. But Al, Mr. Streamer, buffer overflows have been around for a really long time and have mostly disappeared from the threat landscape because of mitigations and code review. Why do we bother learning it? Okay, well, the joke's on you, motherfucker, because just 3 weeks ago, a 0-day was discovered that has existed in Windows for like fucking decades. Okay, a 0-day was discovered that it was a stack-based buffer overflow in the Windows kernel cryptography driver. So these are still being found, even in Windows core functions. These are still being found, and especially in third-party software, IoT is rife with these guys. IoT has so many IoT devices are so insecurely coded, it's embarrassing, okay? Buffer overflows are absolutely fucking everywhere on IoT devices, even very simple ones. A lot of times they don't even have ASLR, let alone DEP, okay? So these are still super relevant, okay? Omega relevant. Like, these still are found all the time. These are found, okay? So there's nothing out of date about what we're going to discuss today. Again, we might not be talking about like the modern day protections you'd have to contend with, but we're gonna crawl, walk, and then run, okay? Shadow Angel 1993, I missed your follow. Cthulhu Fatagan, my friend, good to have you here. Alright, demo time, we're into it! We're done with the PowerPoint, okay? We're done with the PowerPoint, we're getting into it. We're gonna get into it, okay? We're gonna get into it. Do I have any CVEs to my name? I do, actually, but they're not, my name is not written on them. They're in proprietary software that they were discovered on private and paid bug bounting. Dark Eldar, you are right on time. We're about to start the demo. You just missed the boring slides, my man. You missed the boring slides. You're gonna be able to come back and read the slides. It's gonna be fine. Okay? So, what are we gonna do today? What are we gonna do? Using our wisdom, using this eldritch wisdom we have just gone over, we are going to be exploring this. I'll make it bigger so you can see. Can I make it? Is it not going to be bigger? Why? Okay, it won't zoom in. It won't zoom in. Can I zoom? How do I zoom? Okay, well you can't see. But it doesn't matter, you don't have to read any of this! The good news is, you don't have to fucking read any of this exploit because you're not going to need any of this, my boys. I'm going to teach you how to do it yourself. You're going to write all of this yourself. Well, not all of this. Like this one is actually doing version detection. But we're not. But we're going to be writing the core of this. We're definitely going to be writing the core of this. Okay, how it basically works. All right, we're going to write this from scratch in Python. Okay, this is in C. It looks like. Yeah, this is in C. So, all right, WarFTP version 1.65. It's an FTP program. Exists in real life. CVE 2007-1567 was discovered in 2007 then. So, yeah, discovered 2007, March 25th, alright? And we're gonna do it. We're gonna do it, chat. Okay? Here we go. Here we go. We're gonna get started. Get us out of these fucking slides. Get them out. We don't need them. We don't want them. Alright. Here we are! Blast from the past, chat. A blast from the past. Here we are. We are in Windows XP. We got the old hill here. It's really nostalgic, I agree. Super nostalgic. You're going to be able to hear the sounds the whole day. And we're going to open up this folder. I've prepared this, especially. So it looks like FTP daemon and FTP. Okay, these files. Okay, I'm just going to show you what happens if I just open War-FTP. It's going to error, okay? And the reason, it took me a fucking while to figure out what the fuck was going on here. And then I eventually just, I eventually just deleted these. Can I make this font bigger? Can I make this bigger? View. Details? It's not really necessary. It's not necessary. We're not going to be doing much, but, if you have problems, sometimes I have this problem with certain installs, and sometimes I don't. Okay? But ftpdaemon.dat and ftpdaemon.ini need to be deleted every time we restart WarFTP. Okay? Alright, so here's what WarFTP looks like when you start it up. You open the program, this window's going to come up, and then you have to click on this little lightning bolt up in the top left. Okay? Now it's listening. So now WarFTP is listening for connections. And now, this isn't enough. We're not able to, like, see... We don't have the source code of WarFTP, okay? So the first thing we need to do here... The first thing we actually need to do is we need to attach a debugger to it. So we have Immunity Debugger here. Immunity Debugger. Alright? So we are going to go File, Attach, and we are going to... Hopefully this font is as big as I can make it, so hopefully it's big enough for the stream. WarFTP, we're going to attach. So whenever you first attach a process to the process is going to be paused. Notice how it says pause down here in the bottom right. So you're just going to hit. So at this point, we're just going to hit F9 to continue execution. So now notice that pause has changed to running, and WarFTP is now running. It's now executing. It's doing its thing in memory, and the debugger is attached to it. How would we go about this on OSCP? Exactly the way I'm showing you. Exactly the way I'm showing you, Slithering Tupac. Everything I show you here is going to be very similar to what I did on OSCP personally. Alright. So now, the process is executing. So, the debugger allows us to see the process's memory. This is like the process's memory right here. This is its actual instructions that it's executing. Over here is the stack frame. We're just getting acquainted. This is what's going to show us the stack and what's happened to it once we do things to it. These are your registers, okay? And over here is the dump. This is just like the hex dump of all of this. It's just a hex dump view of other things. Really simple, okay? Do not be scared of the debugger. Do not be scared of the debugger. Do not be scared of the debugger. I know this is scary at first view. I'm going to make it real easy for you. I promise you. All right. Let's head into Kali. This is my Kali machine. So we're going to start this up. Got a terminal window open. Make it bigger. Let's move the terminal all the way over here. That's a good spot for it. All right. That's good. All right. Alrighty. So now first we're going to ping. I'm just going to make sure I can 10.0.0. I think it's 13. Yeah. So we can reach my Windows XP machine. And then we're going to go nmap TAC P21, which is FTP's port. We're doing a simple port scan just to make sure FTP is listening for connections, okay? TAC SV 10.0.0.13. Oh, I got to make the font bigger. There we go. Now you can see. There you go. So notice WarFTPD 1.65. And if we connect to WarFTP, if we go FTP 10.0.0.13, notice it gives us the banner. WarFTP 1.65 ready. We can enter a username. Alhazred, and then we can enter a password. And the password was incorrect, so we can't get out. Well, that's it, right? We can't get in. We can't get in. What can we do? We can't get in. Oh, no. The horror. The horror. The horror. Okay, let's just close out of this. Exit. Let's do this again. Except this time, actually, let's get a Tmux pane open. Mukder stream, CD stream. Let's get a Tmux pane open here, like we always do. Tmux new TAC-S stream. Okay. All right. So now we're going to. I'm going to create a new pane. I'm going to go clear Python 3 TAC-C print a times 1,000. Or we'll make it 1,000. Sure, that's not going to be a problem. Print a times 1,000. I'm going to have to need to make these single quotes. So we're just going to have it print out 1,000 A's so I can easily copy and paste this. All we're doing is printing a whole bunch of A's to the console. Very simple. Okay? I haven't lost anyone yet, hopefully. All right? We're going to copy this. Now we're going to go to FTP. 10.0.0.0.13. And we are going to notice it's asking for a username, and we're going to go like that. Let's see, did that actually work? I don't think that actually was going to work, actually. Now that I think about it, I don't think that's actually going to work the way that I was hoping. I should have practiced this before the stream. Yeah, it did not work. But so we need to forge. So basically, what's happening here is that the FTP client is preventing us from sending the maximum buffer. Like, the actual FTP client on our Kali is preventing us from sending all of this. Okay? So we need to forge our own FTP packet. So we're going to write a simple program. Oh, god damn it. Quit. Get out. Okay. Vim crash.py. So we're going to write a Python script. Now, my friends, do not be scared. Even if you don't have any programming experience, that's okay. Okay, I'm gonna do my absolute best to explain everything that this script is going to do at all times. Problem manually entering the size string using netcat. Yeah, you can do it. We can do it with netcat. Let's do it with netcat. That's actually a better idea. Netcat is a good idea. All right, so let's do. I can demonstrate it more easily with netcat. So instead of using FTP, let's use netcat. 10.0.0.13 with port 21. Okay. So now it's asking. Now we have to add user space and then a whole bunch of fucking A's. Now, it did ask for a password. It's going to do that every time. But notice if we put stuff in... Did it actually crash? Let's find out if it actually crashed. It did not crash. It still did not crash. Alright. I must be fucking it up. What did I do wrong? Do I have to actually put the password in there? Does it really want the password? I didn't put the password. Okay, we'll do this. I think you have to actually put the password. I think you're right. Oh. Oh, did it crash? It did. It did. Look. Look, chat. What have we here? What have we here, chat? What font? Can we make this any fucking bigger? God damn it. I can't make it any bigger. Debugging options. It's not debugging options. It's options appearance. Can I make it any bigger? I have it in bold. I have it in, can I make it size 18, maybe? I can. Good. Okay, good. Excellent, excellent. Okay, that's excellent. All right, can everyone see? Why does we see that down here it says access violation when executing 41414141. And as we see right here in the EIP register, up here in our registers pane, EIP has been overwritten with 4 ones. What is 4-1, chat? What is 4-1? Why is it 4-1? 4-1 is the hex value for capital A. And if you look down here at the stack pane, look at the stack pane. What have we done? What madness has befallen this stack pane? It's all 4 ones, chat. What psychopathy has overcome this program? We have overwritten the stack, and with it, one of the return address pointers. We have and when EIP, when the function finished executing, when it finished executing whatever function it was inside to accept the username, it went back to the place on the stack where it saved the return address, but that place has been overwritten by 41414141, and it doesn't know that. So it tried to load a memory address 41414141 into EIP, and then just went there, and then it got an access violation because this isn't an executable part of memory. Is everyone following? Is everyone seeing the madness we hath wrought on this poor program? Is everyone seeing? Is everyone good? Is everyone? We're still here. Yep. Nisrox, don't jump ahead. Don't jump ahead. We're gonna get there. Believe me, we're gonna get there. How did I determine 1,000 A's to overflow? That's just there is not a set number. It's going to depend on exactly how big the buffer is, how the stack is set up, and all that sort of things. I just chose a lot of A's. We're going to fuzz it here in just a little bit to determine just how big of a buffer will actually crash this thing. We're going to fuzz it. Don't you worry. We are going to fuzz it. I'm going to go ahead and fuzz it still, just to demonstrate. Just to demonstrate it, I am going to fuzz it. But this is like a really common input that you could just send just to test. And so sending 1,000 A's is not unlikely as a first thing to send. Okay, so we're going to fuzz it still, but... Alright, so when we restart it, we're going to have to delete... You're going to see this happen about 5,000 times today. I have to delete these 2 files. Okay, delete. Okay. With those files deleted, we can then go Control F2. That will restart the program. Now the program is paused again it's paused at its entry point. And then we're going to hit F9. And you see the War-FTP box pops up again. We hit the exclamation point. War-FTP is good to go again, okay? So that's how we're just going to repeat that over and over and over again until every single time we want to crash this program. All right? So now we want to start working on a skeleton of an exploit, okay? This a way to crash the program with Python, so we can build on that and generate an exploit after a while. Okay? So here's what we're going to do. First, we're going to do Python. If you're not familiar with Python, that's okay. It's very easy to read. So vim crash.py. So the first thing we're going to do is we're going to specify user bin the executable for the program, Python 3. Okay? And then we're going to import socket. I think the only library we're going to need is the socket library. And then we're going to declare our buffer. So we're going to say a buffer equals B. Now it has to be the byte string, so you have to put a B in front of all your strings. It has to be the byte representation of it. Times, we'll make 1,000 right off the bat. We're gonna fuzz it. We are gonna fuzz, but we have to make a program to fuzz with first. I'm gonna explain fuzzing here in just a little bit. Print, and then we're gonna say S equals socket.socket. We're going to create a WebSocket to connect to the box through, to connect to War-FTP through. So socket.socket, socket.af underscore inet, socket.sock stream. Again, we're just creating a TCP socket. This is all we're doing. And then we're going to connect to FTP. So we're going to connect equals s.connect. And this wants a tuple, I believe. So you have to have two parentheses because it wants a tuple. 10.0.0.2213. And then 21 is the port. Okay. So we're creating a socket. Now we're connecting this. The connect method is going to make a connection to this TCP port, port 21, at 10.0.0.13, which is the address of my Windows XP machine. Okay. Then it's going to, we're expecting a banner first, right? So the first thing that WarFTP does when we connect to it is it's going to send a banner. Star is right here, by the way. She's right off camera. You can't see her, but she's sitting on her fancy bed, which is this piece of foam that I got in an Amazon box that she loves to sit on. We call it her fancy bed. Okay, so the response, we'll spell it resp equals s.receive. We're expecting WarFTP to send us some bytes, so we'll just say 1024. That's way more than we actually need, but we'll just that's how many bytes we're expecting to receive. We're gonna print the response, so print resp. Okay, so now we can actually send our buffer, right? Okay, we can actually send our buffer. So the buffer, so we're gonna s.send. B user plus the buffer plus and then we have to send a new line character. So we have to send the new line characters because that's what terminates. That's how you communicate with FTP. FTP understands commands that are terminated in new line characters and carriage returns.
This may come up again later, so I would remember that.
All right. So this may come up again. Like I said, this may come up again. So keep in mind that FTP terminates strings with carriage returns and new lines. Okay? Oh, a card from the fit deck. We're getting into the fit deck already. All right, where are we with Stream Raiders, actually? We have 13 more minutes left. We got 13 more minutes on that sucker. On that sumbitch. All right, here we go. So we're sending the buffer. We sent the buffer. So now we're gonna receive. So response equals s.receive, and well, I guess we'll set it to 1024 again. Accept a kilobyte of data. And then we will... honestly, it shouldn't hit this part of the code, but we're going to do it anyways. Send... it shouldn't hit this part of the code. The program is going to crash before this, but we're going to do it anyways. So B, just for completeness' sake, B pass, and we'll make the password Cthulhu. Password Cthulhu, and we have to terminate it with an r/n. Okay? And then we're all done. We can just close the socket. Oh, I forgot the... did I do this right? Wait a minute. It's indenting. Why are you indenting? What is the confusion? Did I do this correctly? It's indenting, which makes me a little bit concerned. Did I forget a quote? I don't think I forgot a quote. I think I'm okay. I don't know why it's indenting, though. It's making me uncomfortable. Alright, fuck it. We're going to freeball it. Here we go. s.close. Alright, so we don't need a TCP socket anymore, so we can just close it. Alright, so we're just going to... Alright, so now we're going to Python 3 crash.py. And we have WarFTP is running, is it not? It is. So now we can God damn it, I keep clicking the wrong thing. Okay, here we go. Python 3, crash.py. Yep, I did fuck something up. What did I do wrong? Did I put an extra... Oh, I escaped the... Okay, there you go. That explains it. Thank you. Thank you, chat. I should have read chat. I have to do the... I know I have to do the fit deck and the pull-ups. I'm going to do them here in just a second. All right, Python 3. It looks like... Yep. And do we get a crash? Did we get a crash? We do. So we do have a crash. This is excellent. This is quite excellent. So we have crashed the program with our Python skeleton, exploit skeleton. We're gonna turn this into an exploit over time. Please enter your username. I've fucked something up. What did I fuck up? It's the output is not pretty. We can print the response, I guess. Print response. Oh, my music stopped. Bring the music back. There we go. There we go. All right. It doesn't really matter, as long as it's sending the output to the program. So we have our crash. Let's restart War-FTP again. We have to delete those files. Gotta delete these files. Control F2 restarts the program. F9 executes it. Alright, now it's running again. So we have our... let's copy crash.py to fuzz.py. And let's vim fuzz.py. Alright. So... I guess... so we're going to create a very simple fuzzer here, chat. So... Who's the owl? Thank you so much, my friend, for coming. Cthulhu Fatagan, good to have you here, as always. Now, normally, you would use a fuzzing, like, framework. There are plenty of tools out there that will fuzz programs for you. It's kind of silly for me to write my own fuzzer right here, just for this program. Normally, I would use something called boofuzz. But my objective here with this stream is to de-obfuscate this whole process as much as possible. I would rather not use tools like I would rather not use tools when I can avoid it. And in this case, as it turns out, it's very simple to write a fuzzer for this program that doesn't need boofuzz. We'll cover boofuzz and other fuzzers in future streams. But we're gonna write a really simple fuzzer here. Again, someone asked like how I knew to try 1,000 A's. The answer is, well, the real answer is I know how many A's will crash War-FTP. Okay, I just know because I have done this exploit before. But in real life, that's just that's something you would just start off with. You would just send a whole bunch of input to the endpoint to see. Those of you who are here for the other stream, for my last stream 2 nights ago, we encountered a buffer overflow on a Hack the Box machine. And I did 1,000 A's then, I'm pretty sure. And I just copied those A's into the netcat session, and it crashed. So 1,000 A's is just a good number to start with, really. It's just a decent number to start with. But we're going to find out. So from time import sleep. We want the function to sleep between fuzzes. Okay, so... I guess let's do this. What? Oh, I'm in insert mode. Switch to visual mode. Come down here and indent this. Okay. And then we can do while true. We'll make the buffer B. uppercase B times 4, or we'll make it times 10, I guess. Why am I doing B times 10? Well, I'm gonna show you here in a second. Okay, watch it. Watch. Okay, so we'll make it buff equals. I'm hoping this works because I'm just freeballing it, guys. I did not prepare for this as much as I should have. So we're setting our buffer that we're gonna send equal to A times. I guess we can have another variable called I. I equals 0, I guess. A times I plus buffer. I think that should work. And then it's going to connect. It's going to do the whole. And then we'll have a line that says print fuzzing with buffer length plus string of length buffer buff. Okay, and then we'll come down here to the bottom of our while loop and we'll go I plus I plus, I guess. We'll go I equals I plus 100. Okay. Oh, whoops. Okay, we wrote it. All right, so we're just gonna follow this. We're just gonna follow this code logic. First, we're gonna declare a buffer of 10 Bs. Okay, we're making a buffer of 10 Bs, and then we're gonna set a variable, a loop counter of I equals 0, and then we're just gonna enter an infinite loop where we are first generating our buffer, which is gonna be a number of A's times the I value, whatever I is. So the first loop, I will be 0, so there will be no A's. It's just gonna be a buffer of 10 B's, and then it's gonna do the connection. It's gonna it's gonna do the connection and all this, and then it's gonna close it, and it's gonna add 100 to I. This is sloppy. I plus equals 100. Like this. And then it's going to go back and loop again. And this time it's going to send 100 A's and 10 B's. Does that make sense? Is everyone following? I'm glad. By the way, I am... Oh, God. Year 0 found it. Oh, God. We got to do it. We got to do it. Can I even, like, do it without... Can I even... it's going to make me make a new terminal. I'll do it. Hang on a second. Alright, we'll make a new window for it. Oh, we'll make a new tab, I guess. New tab. Kali Light. Oh, God! This is horrible! Oh, Jesus. Why did you make me do this, Year 0? Why? Why? Yeah, Year 0 did this. This is Year 0's fault, okay? So is everyone following... Everyone following the code logic. Switch, yeah, psych. Year 0 switched it back. Oh, no, okay, now we're on terminals regular. We're back to regular terminal. We're back to regular terminal again. Already we couldn't handle it. Already. No. We'll go back. We'll go back. We'll go back. We'll go back. Fuzzed up. Is everyone following this code logic? It's basically just going to send buffer of ever-increasing numbers, of ever-increasing size, until the program crashes. Very simple. Okay, so let's try and do this. Is WarFTP running? It is. Okay, so let's try and do it. So Python 3 fuzz.py go. And I broke something. Something is broken. Did it actually crash? It does not appear to have crashed, even. Is it even running? Can I like... It does not appear to have crashed. I fucked something up. Well, first of all, I forgot to sleep. I forgot the sleep command. You're setting buffer? Did I do that wrong? Yeah, that's probably what I did. This is just part of coding. Yeah, I'm setting buffer and not buff. Yeah, I did a number of things wrong. That's okay. That's why we're here. I probably should have written this ahead of the stream, but you know what? I ain't about that shit, right? I ain't about that preparation shit. We're just doing it. We're doing it off the cuff, okay? And then we're gonna sleep for 2 seconds. So we're gonna have execution sleep for 2 seconds in between connections. So it's easier to read the output. Here it goes. So first it's doing 10, then 110, then 210, then 310. Now eventually the program's not going to respond anymore. Right about now. Looky there. So we tried to fuzz with length 610, and the program is not responding. So that means that this length actually crashed it. Okay? That length actually crashed it. Now, why, you may ask, why did I put those B's at the end of the buffer? Why are the B's at the end of the buffer sitting at the end of the buffer? And that's because I want to now go through the stack and make sure that the entire buffer made it onto the stack. If we have a whole bunch of A's and at the end there's 10 B's, which there is, there are 10 B's at the end, so I know the entire buffer made it into the stack. This is very important when when you need to know how much buffer space you need. Psych! Thank you so much, you psychopath! You're out of control. Psych, Nightmare, and Psych and Nightmare especially are just completely out of control. We had another big gifter today. Who else was the big gifter today? Susvarus as well. Susvarus, you people are Psych is a psychopath. He is consumed by the nethermost confusion of buffer overflows that he feels the need to gift this many subs. Thank you so much, my friend. Thank you for supporting the stream. To everyone else, oh my goodness, what even just happened? How many even? Wait, 50 tier 1 subs. What is this? Cyber insecurity. You madman. This man needs to be disaffected from it. This man needs to be separated from his finances stat. That is a lot of money to give a random hacker on the internet, okay? That is a lot of money, sir. Sir. Hey, Ashantani, my friend. I don't even have, buddy, I don't even have, like, a, you are killing it, keep it up. I'm really glad you're enjoying it, Cyber Insecurity. I'm so grateful to the positive reception my stream has gotten after only a few weeks of streaming. Thank you guys thank you so much, Cyber Insecurity. Get with me on Discord and let me know if there's anything I can do to pay you back, because this is absolutely fantastic stuff. Like, thank you so much. You are so generous. All right. So, as I was saying before everyone went fucking batshit insane, it might as well be I might as well put the fucking chat in sub only mode because you're all subs now. If I put 10 B's at the end and I look in the stack and there's a whole bunch of A's and then 10 B's at the end, I know my entire buffer made it into the stack. Okay? So now, buffer size is very important. The more buffer size we have to work with, the easier it's going to be to exploit this program. This is awesome, and I'm going to let you finish, but you take down the Switch terminal reward, I'm going to ban everyone who wants to change. No, this is fucking hilarious. I'm keeping it. I'm keeping it. You can't make me. You're not my real dad. You're not my real dad. It's as funny as I thought it was going to be, watching the chat battle over the stream, over some people want to torture everybody else, and other people want to fix it. Yeah, he's gonna regret saying that before I spend my entire stream in the light mode. Okay, so now we want to figure out how big can this buffer get before the crash no longer works. Generally, there's only so much buffer space that we're able to send a program. Okay, so let's try and increase the buffer size incrementally until we reach a point where the program either crashes in a different way or doesn't crash at all. So let's first of all, let's restart. Let's restart, delete these, and then we will hit Control F2, and then hit F9, and War-FTP starts up again. We hit that. We're good again. All right. So here's what I did to the program, to the crash. So now we're gonna fuzz. So we know basically that 1,000 bytes works, right? Because we crashed it with 1,000 bytes first. So now let's try 1,100 bytes, 1,100 bytes, and see if it crashes. And see if it crashes in the same way. And the whole, again, it's key to know that the whole buffer makes it into memory. We have to know that the whole buffer makes it into memory. So let's do Python 3 crash.py. Okay, it looks like that worked. Now let's go into, we do see that it crashed. Good. Let's go scroll down through all of our A's that's overwritten the stack. And we see that our 10 B's are at the end here. So the whole buffer, once again, made it into memory. So now, let's try 1,200 bytes. Let's try that and see what happens then. We're just trying to see how big we can make this buffer space. The bigger the buffer space we make, the more leeway we have to work with, the easier this is to exploit. And you're going to see that a little bit clearer later on. So let's first delete those files again, because War-FTP is fucking War-FTP. And then we'll restart it, and we will hit F9 to get it started. There it is. Now we go to we go back here. We do vim crash.py. Again, it's crucial to know not only how big of a buffer we can send, but also how much makes it into memory. Every program is going to be different and is going to accept input differently, and so you need to do all this trial and error to figure out what it'll accept and what it won't. So this time we'll try 1,200 bytes. So we're sending 1,190 A's and then 10 B's. Okay? So let's try to crash it again. We sent it. And what has happened here? This is different. Look. 41414141 is not an EIP. Okay? This says access violation, so the program has crashed. But oddly enough, it did not crash in the same way. Like the return address, the return address was still overwritten, but we broke something. Now it's crashed in a different way. EIP has crashed in msvcrt.dll. What has occurred here? What has occurred?
Put a pin in this. We may come back to it later.
But for right now, chat, we're just going to assume that we can only send a buffer of 1,100 bytes. Okay? Purple Fox is correct. Purple Fox knows what the fuck is up. Purple Fox knows what is up. The stack grows to lower memory addresses, but the overwrite happens in the opposite direction. It will start at the top of the stack and work its way down the stack. Hopefully that makes sense. The stack is not the let's follow this in stack. We don't see the stack does not look the same as it did. There are no A's here. See this? No A's. And that's it because we're in a completely different part of memory. It has crashed differently. Oh, here's our A's. Our A's are down here. But this is nowhere near the stack pointer. This is nowhere near the stack pointer. The stack pointer is all the way up here. The stack pointer is all the way up here. Our A's are all the way down here. So ostensibly, chat, there's nothing we can do with this. Ostensibly, I got you. Don't worry. Don't worry. There's something we can do with it. We're going to come back to it. All right. So for right now, just assume that we can only send 1,100 bytes. Okay? We can only send 1,100 bytes. So let's do this again. Let's restart the program again. Delete those. Control F2. Start it up. Okay. Now it's running again. So we can only send 1,100 bytes. So we can copy crash.py, exploit.py. We'll vim exploit.py. So we don't need these B's anymore. We can send So now, okay, I'll let you guys now that we know how many bytes will crash the program, what is next? Cat exploit.py. What is next? I heard someone said it before. Someone said it before. What do we do next? What do we need to find out next? We know the exact size. Do a wink reward with channel points. Like, my channel points are going to be a gigantic clusterfuck later on. Ong31D is correct. Where is EIP is stored? Year 0, also correct. We need to find out. I think I already restarted the program, but we need to find out which one of exactly. There are 4 of our A's. Exactly 4 of our A's are overwriting a return address and are ending up in EIP. We need to figure out which 4 A's that is. So the way we can do that is we generate a buffer size of 1100 bytes, but instead of all A's, we're going to send it a cyclic pattern that is non-repeating. And let me demonstrate what that is. So let me demonstrate what that is. So we can use MSF has a tool for that called pattern create. Now there are going to be those of you who are like, Mr. Streamer, Mona.py can do that. Why don't you just do it with Mona? Because we're going to talk about Mona. We're going to talk about Mona. Okay, believe me, we're going to talk about Mona. But it makes more sense to do it over here in Kali because that's where our exploit's being written. Mona is sitting over on the Windows machine. Okay, so MSF pattern create tac h. So we just needed to add a length. So we want a length of 1100 bytes. We want to send it 1100 bytes. So notice it sent a uppercase, lowercase. It sent a pattern. This is a pattern of bytes that is non-repeating. So that later on, so we're going to put all of this into the buffer, and then some of these bytes are going to end up in EIP. And then by the bytes that end up in EIP, we're going to be able to figure out exactly how many bytes into our buffer EIP is being overwritten. The return address is being overwritten. So we're going to take this. We're going to copy that. We're going to go vim exploit.py. We don't need this buffer. We're going to comment this out for right now. And then we're going to go buffer equals, we need a byte, like that. And then I'm going to go set paste. And then control shift V. Whoops, I fucked it up. Hit undo. Undo. Put it there. And then we want to hit enter insert mode, control shift V to paste, and I fucked it up again. But so this time I'll just do it the long way. There you go. Oh, no, like this. That. Oh, and then I fucking put a double quote at the end. Put a single quote. There we go. All right. So now this is our new buffer. Still the same size. It's still going to crash the program, but depending on which letters and numbers end up in EIP, we're going to be able to determine how many bytes into our buffer EIP is being overwritten, so that we can then put a memory address there to be executed. So that's what we're doing right here. And this buffer, this is commented out. This is not being set right now. So we're going to... Did I already start the program again? I did. So Python 3 exploit.py. Okay. Okay, so the program crashed, and this time, what's in it? 3271 4131. Okay, so now those are the bytes that ended up in EIP. All right. So now we go back here. We go back here and we go MSF pattern. Is it locate or is it pattern offset? Yeah, offset. MSF pattern offset. Put in the length of 1100 bytes and tac q for query. And what was the exact number? 3271 4131. 3271 4131. So this says there's an exact match in the pattern at offset 485. It should work without the L. It probably would, yeah. So that means 485 bytes into our buffer is the return address, which is overriding EIP. That was Algebra 97. That was probably cyber insecurity. The man was a complete madman and gifted 50 subs earlier. The psychopath. He's out of control. He needs to be separated from his finances, honestly. It's a lot of money to give to a crazy hacker on the internet. Alright, so... okay, alright, so we have... so now we go into... So 485 bytes into the buffer. So we're going to vim exploit.py. Okay, we're going to comment this out now. And so what we're going to do... Then we're going to uncomment this. And we're going to put A times 485. Plus B times 4 plus bytes plus we can do it this way. We can do byte C times and we can do 1100 minus 485 minus 4. So what have I done here? So basically, the buffer is still going to be 1100 bytes. This buffer is going to need to be is still going to be 1100 bytes. The first 485 are all going to be A's, and then the next 4 are going to be B's. If we've done it right, if we've done this correctly, then 4 B's should end up in EIP. Does that make sense? 4 B's should end up in EIP. And then we're just padding out the rest of the 1100 bytes with C's. Is everyone following what this code is doing? Does anyone, if you have questions, ask. If you have questions, ask. Why C? Just because we can see the different, it lets us clarify which part of the buffer we're looking at when we're looking at the buffer in the stack. It just makes it a little clearer. Okay. So, Python 3 exploit.py. Is it running? Did I start it up again? I did not. So I have to start it up again. We'll delete these files for the millionth fucking time. Delete. Okay, and now we will Control F2 to restart the program. F9 to run it. Okay, it started, it's running. And now we're going to destroy it again. This poor program. Alright. So we're going to go back and look. And we see, look, now it's overwritten with 42424242. What is 42? It is B. It's capital B. So we have determined the right 4 bytes in our buffer that is overwriting the saved value of EIP. Okay? And now if you look down here, we're going to leave this open so I can continue to demonstrate what the fuck is going on here. If we look down here, we see that on the stack, we see that here's our A's, here's our 4 B's, and here are the start of the, here's our C's. And we also see, interestingly, that ESP is pointing at these C's. This is very interesting. ESP is pointing at these C's. So basically what we need to do here right now, chat, is place an instruction in EIP into this. We need to replace these B's with a memory address. 0day99, thank you so much for the follow, my friend. Cthulhu Fatagan, good to have you here. What is C? What is C? What do you mean? What do you mean by what is CEH? The cert? The cert? Oh, SEH. Don't talk about these crazy lunatic concepts in chat. These advanced terms. We'll talk. SEH is a topic for another discussion. We'll get to that. We're not dealing with SEH right now. Don't get confused. All right. So we need to put them now instead of these B's. There needs to be a memory address here. Okay? There needs to be a memory address that's gonna send the program to a place in memory that we control. That place we control is our C's. Our C's eventually are gonna have shellcode in it, like shellcode, that like actual reverse shellcode, and our B's need to send execution to those C's. Does that make sense? Is everyone following? is this is a little bit interesting. So this tells us this is where the stack pointer is right here. This is ESP -4. This is ESP -8. This is ESP -12. Yeah. So that's kind of cool. It makes it a little bit more visual. That's fine. We can do that. Okay, that makes it a little bit more visual. That's today I learned. I need to add like one of those a sound effect for the more you know. Da-na-na-na. Whenever someone teaches me from something from chat, that's genius. I need to do that after the stream. Okay, so is everyone following what the goal is? The goal is to place a memory address here that eventually drops us here into our Cs. Are you following? And the amount of space you have for your C addresses is determined by max buffer size before it crashes differently. Yes. If we didn't have many Cs, like let's say our Cs cut off right here and we had a really small buffer size, we could do our As still. We could find a way to do our As. It would be harder, but we could do it. But right now, this is very easy. We need to find an we need to find an assembly instruction in this program somewhere that executes a jump ESP. Jump is redirects execution from one place in memory to another place in memory. Okay? So by retaining EIP, we know that our Cs are within the buffer size. Yes, correct. What's the importance of crashing differently? Hold off on that. Hold off on that. We're going to talk about that weird crash that we saw, okay? We're going to talk about the weird crash that we saw at 1200 bytes. I promise you we're going to discuss it. Right now, like, don't erase that from your mind. Erase that from your mind. We're not thinking about that right now. We're focused on this. On this crash. That is a different crash. It is exploitable. It's exploitable in a different way. The C's are at the are lower in the stack than this. This is the top. A's are at the top of the stack, and the B's and the C's are at the lower part of the stack. The stack grows to lower memory addresses. Okay? So the first thing before we do anything else, we want to think about bad characters. And now you OSCP hopefuls, better listen the fuck up, okay? Listen the fuck up. This is the second most commonly fucked up thing on OSCP, I guarantee it. Everyone who's ever asked me for help on the buffer overflow for OSCP, the second most common thing that I hear people have misunderstandings about is bad characters. Maverick, I'm glad you're getting a lot out of it. I'm really glad. I'm really trying to make it as approachable for OSCP hopefuls as possible. Bad characters is important. What is bad characters? What are bad characters? Bad characters are any character that either terminates your buffer for whatever reason, or it gets mangled, or it changes your buffer in some way, or it does some undesirable thing to your buffer. Okay? And these are going to be different. These are going to be bad characters are going to be different depending on the program. Depending on the program you're operating with, and bad characters are going to function differently. They're always something that they're not really something that can be predicted. They're something that need to be tested manually. There are a few characters that are almost always bad, and we're going to talk about that. We're going to talk about what characters you can expect to be bad almost every time. But you need to know how to test for bad characters. Okay? So, let's go back to let's restart this machine first of all. Let's restart this. So first thing we're going to do before we do anything else is test, before we start putting memory addresses and shellcode into our exploit, we need to determine what characters are allowed. Because we don't want to find a memory address that we want to jump to and have it and find out it has a bad character in it at some point. Okay? That would be sad. We don't want that. Oh, look who showed up. She's walking right in front of the screen and you guys just can't see her because she's underneath the camera. So, the first thing we need to do is we need to restart the program first. And then we're going to figure out the bad characters. Alright. Head on over here. Now there's a... we need a list of all hex characters between 00 and FF. Okay? We need a list of all characters between 00 and FF. So we can do that with Python. We can do... let's do this in a small script because the interpreter will fuck it up. So it's vim gen bad char gen chars.py. I'm gonna do a really simple script. Import sys. We need the sys.out.write. For x in 0 to 256. 256 is FF in hex. FF is 256, okay? I know hexes gets confusing for people, but hex is just a number. Hex numbers are just numbers like the numbers that you know. They're just base 16 instead of base 10. So FF in hex is 256 in, I guess, normal numbers. Twitch me cool, thank you so much for the follow, my friend. And I think I missed H7CV. Thank you so much for the follow, my friend. Cthulhu Fatagan. So we're just gonna list off all the characters. So we're gonna do sys.stdout.write. And then I know someone followed. Let me just get this out. I'm thinking about this. We want to do a we want to indicate it. We want it to have a backslash and an X, and then we want to add 2 digits, so 0.2. No, it's colon 02 X. Yeah, because X means hex. Okay, and then we close the braces, we close the quotes, and then we need to do it with format. Format X. Okay. I think that should work. Really simple program. So basically all this is doing is it's going to print all the hex characters. Exactly. Codename root already got it. Codename root is doing it. That's what it's going to look like. Python 3 genchars.py. And that fucked up. What'd I do wrong? For x in 0 to 56. Oh, range. Range. I forgot to add range. 0 to 56. So yeah. Okay. So notice its first one is 0, 0. First one 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, all the way up to FF. Are you following me? This is every possible character value a byte can be. A byte is a value between 0 and 256. These are all of the possible values. Now, for the sake of the stream, I'm not going to alter these at all. I'm going to put these into the buffer, and we're going to try and see, and we're going to see what happens. But as I'm going to point out, there's at least one character that can be removed from this basically by default, like 99.9% of the time. And chat is already indicating it, but I'm just going to show what happens if you don't realize this. And it's very common for people to not realize this and fuck it up on OSCP and get really confused, okay? So focus on this. Here's what happens if you... here's what's going to happen if you just put all the characters in there. So we're going to do vim... So we copied this, right? Yeah. Exploit.py. We can get rid of this. dd. Okay. And then we can do another variable, bad chars equals b. And then we can set paste. Control-Shift-V. What just happened? What just happened? I messed it up. I fucked it up somehow. Alright. Let's do nano exploit.py. Alright, bad chars equals... It's harder to fuck up in nano with the copy and paste. Okay, there it is. I know it can't be read. We're just going to put the closing quotes. Let's go back to home. I forgot to put B, predictably. So we'll put it there. We'll write this, quit, and we'll vim exploit.py. So now you can see it a little bit easier. We can get rid of this. We don't need this anymore. This is just going to confuse people. All right, there we go. So now all of the bad chars are in there, 256 bytes of them. Let's see, who we got? Teletops, Bad Chaz RT, Holden, Incognito 1184. Thank you for the follows. Cthulhu Fatagan, my friends. We're battle ready in 5 minutes. Okay, we got time. All right, so these are the bad characters. All right. So we're gonna. how do I want to do this? I want to put these at the end of the buffer to make sure it still crashes. So we're going to do, we'll add minus length of bad chars, even though I know it's 256. Yep, and then we'll add bad chars onto that. Okay, so these are all going to be at the very end of our Cs. Okay, very end of the Cs, as long as I calculate this correctly. So 1100 minus, yeah, that should be okay. All right, we'll try that. Oh God. Oh, no, it got countered. It got countered. Never mind. Never mind. Paperboy Gold. Paperboy Gold just burned 4,000 points just out of nowhere. Can you explain why 2 chars and not 4? What do you mean by 2 chars and not 4? What do you mean by that, Poker Nabi? Explain on that question. You mean like why are there 2 characters? These are hex. These are not characters. These are hex numbers. These are numbers in hexadecimal. Do not think of them as characters. These are hex. These are hex numbers. It's like the difference between 3 and 33. Okay. You wouldn't say 33 has 2 characters in it, even though it kind of does. 33 is just a bigger number, so it has another digit next to it. Does that make more sense? Did I mess up this? Did I mess up quotes? Did I mess up quotes? I don't think I messed up quotes. The quotes look okay. All right, let's try and Python 3 exploit.py. Now it should crash for us. It does crash. So now what do? We're going to follow that. We're going to follow ESP and dump. So we're going to bring it down here. So let's make this a little bit bigger so we can see it. Oh, that's not right. I want to make this pane bigger. Here we go. So here's all of our C's. Let's make this a little bit bigger so you can see the ASCII. Scroll down. And at the end of our C's, that should be our characters. But notice there are no characters. Why are there no characters, chat? Why are none of our bad characters appearing in our buffer? Why? Ragnarok, Ong31D, Purple Fox, these are all correct. These are all correct. Because the very first character is this, a null byte. As I said very briefly during the slides, a string in C is made up of it's an array of char values. It's an array of chars. Char is a shortened version of word of character. So if you have an array of 15 chars in C, that's your string. It can only fit 14. It can only fit 14 characters in that string because the 15th character is a null byte. The null byte terminates the string. Otherwise, C doesn't know where the string ends. C can't figure out where the string ends unless there's a null byte at the end of it. Okay? So, what's happening here, since War-FTP is written in C, what's happening here is that our buffer is being terminated at this null byte. This null byte is terminating the string. So it is not, the buffer is not appearing in our payload. So, how do we fix this? We simply remove, so we now know and we can write down that 00 is a bad character. That null byte is a bad character. Now, you can pretty much just assume this, chat. For like in like 99% of the time, the null byte is gonna fuck your shit up. Okay? The null byte is gonna fuck up your buffer. So just so if I was doing this on my own, I would just remove the null byte, like just at the outset. So now let's do it again with the null byte removed. This is the process. This is the process of discovering bad characters. We're just going to send this whole buffer in, and every time we're going to examine what makes it into memory, and we're going to remove any character that is either mangled or terminates the string or does anything bad to our buffer. And we're just going to keep removing characters until the whole thing makes it in. And that's how we know what the bad characters are. And I know it's laborious, it's painful, but that's what this is, man. That's hacking, baby. That's hacking, baby. All right, here we go. Get in. Let's leave the dump. Let's leave the dump open like this. We have to start this up again, so which means I need to fucking I closed the folder because I'm an idiot. This needs to be removed. Delete. All right, we'll restart WarFTP. F9. WarFTP starts again. Start it up. Okay, let's crash it again and see what characters make it in this time. Okay. Back up. So now, we've crashed again, we see. Follow and dump. Let's go down to the bottom of our Cs. And now we see, right down here, we see these are the end of our Cs right here. GUI Senpai. Paperboy Gold is keeping the Kali terminal in light dark. I keep not looking at it when people change it. Sorry about that. So notice that the first character, 01, made it in. So why are we trying to find bad characters and removing it? Because we don't want those characters to appear in our shellcode later. If these characters appear in our shellcode later, it's going to break, it's not going to execute, and we're not going to get a shell. The shellcode won't execute if it has bad characters. It'll malfunction. So we need to figure out what characters are bad so we can exclude them. So 01, 02, 03, 04, 05, 06, 07, 08, 9, and then notice it goes up to 20. Hex doesn't go 09 to 20. What comes after 9 in hex? What comes after 9 in hex, chat? A. 0A comes after 9. That is 10. And that's the A is the equivalent of normal numbers 10 in hex. Okay? What is 0A? What is the ASCII character for 0A? What is it? What ASCII character is represented by 0A? Fluffy Squirrels got it correct. Fluffy Squirrels is correct. It is a new line. Let me demonstrate. This character. This one right here. This /n, the \n, the new line character, that is represented by the hex number A. Okay? The hex number A. So, as I said, that since we are submitting our buffer in an FTP terminal, 0A is terminating our buffer because it's like a press of the enter key. It's a press of the enter key, essentially. It is interpreting that as a press of the enter key, and it's terminating our string at the 0A. So we need to remove that. We can just return... I entered visual mode. Get out of visual mode, sir. Thank you. All right, so we'll scroll on over to 0A. We don't want that in here. And I see some of you are already jumping ahead on me, but we're going to go ahead and do it. Or I'm going to continue anyways, because again, you need to do this on OSCP. This process must be followed on OSCP. Absolutely must be. This is the process of OSCP. You have to remove every bad character and then see if it crashes, and then make sure that every single character is making that you have in your payload is making it into memory properly. If you don't, and there's a bad character in your shellcode, it's going to fail, and you're not going to know why. It's going to fail, and you're not going to know why. It's very frustrating having to debug this, especially if you're in the middle of a very stressful exam. Okay? So. I would normally write down the characters. I know what the bad characters are in War-FTP, so I'm not going to bother writing it down. I won't forget any of them, I promise. What are you doing? What are you, this, look at her. Can you see her? She's just rolling around in my chair. Oh, she got down because she was shy. I guess she got down. She was just rolling around in my chair. Just like a crazy person. I looked at her and she went, "Air!" Like she's like, "What are you looking at me for? You weren't supposed to see this." Yeah, I have an RGB keyboard. It is a fact that all of your computer components are faster if they have all pretty lights on them. It is a fact. Delete. We'll start the program over again. There we go. All right, so we've removed 0A now, so let's now send our next payload. Let's go back. Let's go back. Let's go back. What do we got this time? Let's follow this in dump. Head on down to the bottom of our Cs. Now we see 0A has been removed, so the next one is 0B, 0C, and then we're back to nothing. What comes after the character that comes after 0C is 0D. What is 0D, chat? Some of you jumped ahead on me. That's okay. What is 0D? It's a carriage return. It's this /R carriage return. The carriage return character moves the cursor to the beginning of the line. The new line moves the cursor down a line, and the carriage return moves the cursor to the beginning of the line. So a /R and a /N in sequence is a press of the enter key. So both of these characters individually are terminating our payload. So we need to remove 0D. Got to remove 0D. So now we'll see what makes it in. And this time it's going to be a little bit different, chat. I'm gonna spoil it a little bit, and I'm gonna say that this time it's going to be a little bit different, and we're gonna have to. Fortunately, you're not gonna have to go through the mayhem that I did of figuring out why, because I'm gonna tell you why it is. But it was a pain in the ass when I had to figure out why this was. All right, so let's restart this again. Delete. Control F2. F9. Starting up WarFTP again. All right, now let's send the payload again. Okay, let's go back, and we see that we did not crash. WarFTP is still running. We didn't even crash this time. We've removed the bad characters. The buffer's making it into memory. Why? Why isn't it working? I don't expect anyone in chat to actually know this time. If you go back to, but it seems that since we didn't overflow the buffer, our buffer is not in memory. It's not here. It's not there. It's nowhere. We did not overflow the buffer this time, so our input was refused for some reason. It was refused. Okay? Our input was refused by the application. So let's go back and notice we actually got a response from the application. Look. Illegal username. Illegal username. There is a character in here that is not... No, the buffer is large enough, Johnny Sioka. There's a bad character in the username. One of the characters that we are sending is not allowed in usernames. And we weren't seeing it before because it was being terminated from the end. So I'm going to skip the process of doing all the recent reading on WarFTP that I did to figure out what bad characters are in the username. The bad character is the @ symbol. Like the email @ symbol, that's what it is. Okay? Which is hex value 40. Okay? So let's go into here. I promise you, again, it took me a while to figure this out. I had to read the documentation, and I eventually was able to find it. The @ symbol is a bad character in WarFTP. If you couldn't read the documentation, what you would have to do is cut this input in half, cut half of these characters out and see if it's in, and see if the program crashes. Is the bad character either in this half or this half? And then you would continue cutting it down until you figured out exactly which character was breaking it. But in this case, we're going to skip that whole process because I already did the research for you. So this time, it will crash. It's still running. It didn't crash before. All right, so we'll send it. So notice we did not get illegal username, okay, this time. And if we go back, and we do see it did crash again. And this time, if we go to ESP and we follow in dump, we see that here's all of our characters. Now, if I was doing the OSCP exam, you're going to want to literally sit here and make sure that every single fucking character is in here. Do it. I know it's a pain in the ass. Look at me. OSCP takers, look at me. Do what do not just glance over this and say, okay, I made it all the way down to FF, so my whole buffer's in here. No problem. My whole buffer's in here. No problem. No, you must, on OSCP and in general, you must personally... honestly, you can do a Mona compare. You can do Mona compare. If you want it, but Mona is not available to you on the OSCP exam. I think you can make it. You can put it on the debugging box, but I didn't use it for my machine. But no matter what you do, whether you use Mona or whether you use your own goddamn eyes, you need to personally go and make sure that every single hex character is making it in. Okay? You need to personally go through and make sure that every single hex character is making it in. In this case, I'm just gonna skip that part and tell you that it indeed is. All of the characters are in. The only 4 bad characters are the null byte, the carriage return, the line feed, and the @ symbol. Mona is available. I think you can use Mona, codename root. You can use Mona. But it is not available on the debugging machine. You would have to move it to the debugging machine and then put it in. I don't even think you have immunity on the debugging machine in OSCP, but I took it years ago. I don't know what is actually on the OSCP exam now. But Mona, you can use Mona. It's just not on the debugging machine by default, so you're going to have to put it on there. They put it on now? Is that right, Ishcase? Well, I'm not going to speak to that. I took OSCP years ago, so I wouldn't know. But whether you use Mona compare or not, you're going to want to go through and make sure that every single one of these things is in memory. Because I've seen people fail because they missed one. Okay? It is very easy to fail because you missed a bad character. Make sure that every bad character is in there. Or every character made it in. In this case, I can assure you that it is. Could I use Ollie debug? You could. Alrighty. So, we know our bad characters. We know how big our buffer is allowed to be. We know how far into our buffer EIP is overwritten. What do we do now? What now? What do we do now, chat? Ragnarok 08 is correct. We want to find a jump ESP. We want to find an instruction somewhere in one module, executable module that's loaded into memory, that's going to put us at our Cs. Our Cs are located at ESP. This is ESP right here. Our Cs are, well, it's 4 bytes into our Cs. But our Cs are here. Spirit Island, thank you for the follow, my friend. Cthulhu Fatagan, good to have you here, my friend. We want to put a memory address in EIP, which points to a jump ESP instruction. Okay, we want to point to a jump ESP instruction, because jump ESP will redirect execution to wherever ESP is located. It will just take what's in ESP and load it into EIP, which will put us in our Cs right here, which is exactly what we want. Okay, so that's what we're going to be looking to do. So let's do that. Now we can. I'm going to show you the manual way to do this, and then we're going to do it with Mona. Like you can go to View up here and go Executable Modules. Now, when you're looking for memory addresses of instructions, when you're looking for instructions to execute, you want to try and pick stuff that's either in the executable in the actual executable you're exploiting, or in you want to ideally pick something that's in the executable you're exploiting. Why? Because if we just pick any old jump ESP somewhere in executable memory, the exploit will work fine for us probably. But if someone else does it on a slightly different version of Windows XP, like Windows XP SP2 or something like that, Service Pack 2 or something like that, it might not work because the module is in a different place in memory. So you want to try and pick either the module in the module that is that you're trying to exploit, or you want to pick a relatively stable module that's not changed very much by Microsoft, like msvcrt.dll. msvcrt.dll has a lot of useful instructions in it, and they don't change it very often. So first, let's look at War-FTP. Let's load up this. So right here, in the CPU pane here, in the top left, this is the CPU pane. We are looking at the assembly code of the War-FTP.exe executable. This is all of its code in assembly. So we can now go to this. We can now search for command, and we can search for a jump ESP. Now, it doesn't have to be specifically a jump ESP. There are plenty. There is no ASLR in XP. That's correct. ASLR is post XP. Windows 7 has ASLR. Jump ESP. It doesn't have to be Jump ESP specifically. There are other versions of there are other similar assembly. There are other equivalent assembly commands, I should say, that will work. Like for example, a push ESP and a RET. If you have a push ESP followed by a RET, that will work as a jump ESP. That will do the same thing. But we'll just look for a jump ESP. We don't find it. It says item not found. So we'll try a push ESP and a RET. Sequence of commands: push ESP and then RET. And we don't find it. Okay, so if you want to do this manually for some stupid fuck reason, you could go through every module in memory that is like you could go through all the modules in memory and look for jump ESPs or their analogs, or you could just come over here and go Mona. You could use Mona. Mona is not installed by default in Immunity Debugger. You have to go to Mona's GitHub page, search for Mona GitHub, and you'll find it. So you want to go to Mona, jump tac R ESP, I think that's the. Okay, it's frozen up for a second. Okay, so it did execute. It just froze up for a second. So if we go over here, we see this is Mona's output right here, the log data. And it sees it has a bunch of pointers for us. It found a total of 93 pointers, and it says only the first 20 pointers are shown here. For more pointers, open the logs directory. So I open up my logs. We don't want to open up that one. We want to go to my computer, local disk, logs, WarFTPD, jump.txt. All right. So can I make this bigger? Font. Okay. All right. So you guys see this? This is Mona's output. It has searched all of executable memory for jump ESP, for either jump ESP, or it's or call ESP, that also works, or push ESP followed by a RET. So again, there don't seem to be so I'm looking for WarFTP.exe. And I'm not seeing it. I'm not seeing WarFTP.exe. Okay, so if you don't see WarFTP.exe, what you want to try and use is msvcrt.dll. This module is not changed very often by Windows, so it's fairly reliable. This push ESP RET and msvcrt.dll should work fine. Any of these push ESP and followed by a RET should work in msvcrt.dll. He teaches a lot more than most training I've done. That is so kind of you to say, EdgeCase. I'm so glad you're enjoying it. Radaza89 and R. Greiker. Thank you so much for the follows, my friends. Cthulhu Fatagan, good to have you guys here. Okay, so we're going to use this memory address right here. All right. What do you want? What? She is, you can't hear her, but she is just babbling. What do you want? You want to go out? I think she wants to leave. There you go. Go ahead. I think she has to go to... Oh, she has to use a litter box. That's where she's going. Okay, the door was closed and she has to use a litter box. Okay. All right, so we also want to be cognizant that we don't pick any memory addresses that have any of our bad characters in them, okay? So we see that this does not have... our bad characters are 00, 0A, 0D, and 40. And none of those are in here, so this will work just fine. This address right here will work just fine. So we're going to copy this. And we're going to head on over to do I have clipboard set up? I don't think I have the clipboard set up, so I'll have to write it out like a scrub. Okay. Oh, I do have the clipboard set up. Okay, cool. Okay, so that's the memory address. So we're going to do vim exploit.py. So we can get rid of the bad characters. We don't need these anymore. So we can add a variable in here. Return addr is equal to Okay. Now I know that some of you more knowledgeable people in chat are probably already typing to let me know that I'm doing something wrong. But, yeah, Ong31D, shush! Shush! Do not spoil it. Do not spoil it. You guys are spoiling it right now. You're spoiling it. Okay? Just work with me right now. Work with me for a second, okay? We're gonna add that, and we're gonna replace our B's. We're gonna replace our B's with our return address here. So return ADDR. I'm going to demonstrate to you one of the most common mistakes in OSCP. This is one of the most common mistakes, another one of the most common mistakes in OSCP. We don't need bad chars anymore. We can get rid of this. And we don't need this anymore. The rest of that should be correct. Okay? Now, this exploit is not going to work, and I'm going to show to you, but I'm going to demonstrate to you why it's not going to work. All right, do we restart? Is the program running? It is not. I have to restart it. Okay. Let's delete these two files as we have done the entire evening. I feel like my entire evening has been deleting those files. Control F2 restarts it. F9 starts it up. And now it's running. So now we're going to exploit it, and we're going to see what happens. Let's set a breakpoint just so I can illustrate it a little bit better. Let's set a breakpoint. Breakpoint, whatever the memory address was. It was, yeah, 0x77C35459. Okay. Let's just to prove to you, let's browse to that in this. So this is going to allow us to search for a memory address, and so we do see that located at that memory address in memory at this memory address, there's a push ESP followed by a RET. So what's going to happen is this memory address is going to end up in EIP, or ideally this memory address will end up in EIP. Okay? Then the CPU is going to come here and say, "Oh, push ESP. Okay, let me just go ahead and push my ESP onto the stack, and then we'll RET, which is going to pass execution to wherever ESP was. It's going to pop ESP back off of the stack, pop the value that was in ESP right back off of the stack, and then pass execution to that space, to that address. That ideally is what's going to happen here. So let's go ahead and send it. Okay. Have we hit our breakpoint? We have not. We have not hit our breakpoint, chat. Something is wrong. Something is wrong, guys. What have we done? It says access violation when executing 5954C377. What has happened? What has occurred? Compare. Okay, I'm just going to write down what just happened. Let's bring up a quick notepad stream. Get rid of this. So our return address is this. It just crashed at what has happened? What is this? Someone in chat clear me in. What has happened here? It seems that our bytes have flipped around. What black magic? What black magic has changed our return address, has flipped our return address? So, everyone in chat is saying it. This is the phenomenon that is known as endianness. Endianness. Not Indianness. Endianness. E-N-D-I-A-N. Okay? There is a dispute in the computing world of when you are storing bits in memory, do you store the most significant bit? As in, this is the most significant bit. The 77 here is the most significant bit. Do you store that first, or do you store the least significant bit first? Intel is little endian. This is a Intel architecture, so this is little endian. So what has happened is it has stored the bytes of our return address in reverse order. So we just need to reverse the order of the bytes and it will work correctly. It's as simple as that. endianness is something you need to keep in mind for OSCP purposes especially. So just so I don't forget. So it starts with x59, x54, xc3, x77, and then we can come back and delete these. So now we've reversed the bytes to be a little endian format. And now when we restart the program again, there that is. We can run it. Okay. Now we're going to set our breakpoint. We will have to set the breakpoint every single time we try to do this. Every single time we do this, because every time you restart the program, it clears all your breakpoints. So you will need to set the breakpoint every time. So we're going to send the exploit. Now we see, look! I don't know if you can see down here at the bottom, but it says breakpoint at msvcrt 77C35459. And if you see up here in the CPU pane, we have hit our breakpoint. And the debugger has paused execution because it hit that address. Does that make sense? Is everyone following? So now, if we proceed, now I want you to look at what happens to the stack here as this happens. So here's the stack pointer. This is this highlighted thing is the stack pointer right here. So the first thing that's going to happen is it's going to execute a push, or we're going to execute an F7, and then it's going, so notice, it has pushed ESP onto the stack. So this address, the address at the top of the stack now points to the beginning of our Cs. You can see this on the side. And now if we execute this RET instruction by pressing F7 and stepping forward one more instruction, we now see in our CPU pane, we are now at the beginning of our Cs. Like magic, chat, we are now at the beginning of our Cs. So now we can just throw some shellcode here and it will execute. ONG31D. ONG31D. I'm gonna start timing out ONG31D every time he takes my thunder out and spoils it. Okay? ONG31D is out of control. No, it's cool, man. It's cool, man. I'm just teasing you. But he is jumping ahead on us a little bit, okay? It's not quite as simple as what I just said. It's not quite as simple. But I'm going to demonstrate to you what happens when you do it the wrong way. This here that we're about to cover is the most messed up thing on OSCP. The most screwed up thing on OSCP is what I am about to cover. Take notes on this. Take notes, okay? So now, we need shellcode. So we need to generate shellcode, okay? So we can use msfvenom for that purpose. So msfvenom, tech A for architecture x86, tech P, Windows, shell, reverse TCP. This is an unstaged reverse shell. It'll just connect back to us and spawn a command prompt. That's all it'll do. Localhost. What is my IP address? 10.0.0.38. Local port. We'll make it 4444. Exit func equals thread. So you want to change this so that ideally, if you do exit func equals thread, the program will not crash when you close out of the shell because your shellcode will run in a different thread. That won't work for War-FTP for reasons, but it's still good to put in there just as a force of habit. Okay, then we have to put in TAC B. specifies our bad characters. What characters are not allowed to be in our shellcode? So the no byte, the @ symbol, the carriage return, or that's the line feed, and then the carriage return. And then we want it in Python format. Purple Fox, thank you for the 100 bits, my friend. Cthulhu Fatagan to you. It's good to have you here, as always. So now we're waiting a minute. It's going to generate our shellcode for us. So msfvenom is going to use different encoders until it finds one that it's able to encode without these special characters in it. So let's scroll back up. So this is key to point out. Oh, it looks like it used call for dword zor. x86 Shikata Ganai failed. A valid opcode permutation could not be found. That's the first time I've ever seen that happen. Maybe a different port? I mean, it's not going to matter, chat. To be clear, this does not matter. I've just never seen Shikata Ganai fail like that. It could be that the port number is preventing it. Let's see if Shikata Ganai succeeds this time. It really doesn't matter, like I said. No, Shikata Ganai failed again. I guess it just really doesn't like it. So it's key. What's key to note here is that that our shellcode has been encoded. Like when you see this stuff in memory, it's just going to be a bunch of fucking gibberish. It's going to be a bunch of instructions that make no sense and don't do anything because it's all encoded. And it needs to be decoded before it can run. So the beginning parts of this payload are going to be what's called a decoder stub. Did I put an extra 0? I did put an extra 0. Good call. Good call.
Listen to the ending.
I did put an extra 0. It's a good call. Whoopsie daisies. It might not have mattered. Was there a 4-0 in this payload anyways? There might not have been a 4-0 in this payload anyways. We'll make it 4-4-4-4 then. Thanks for catching me on that, chat. Another card from the fit deck. Alright, we're up to 5 of those. The back part of this stream is going to end up being all fitness stuff. Alright, so I think that looks like Shikata Ganai to me, so... Okay, so it did. This time Shikata Ganai succeeded because I didn't fat finger one of the bad bytes. So what's notable about this is that this shellcode is encoded. So the first part of the shellcode is going to be what's called a decoder stub. That decodes the rest of the shellcode. Okay? We're going to copy this. And then we're going to go to vim exploit.py. Shellcode equals B. Control-Shift-V. Oh, I fucked it up. I can fix it though. Okay. So it's basically, this is all of our shellcode. It's in a variable called buff. You can change that variable, by the way. I just didn't care to. Plus buff plus C minus 45 minus 4, and then we have to add tech minus length buff. Alright. So it's going to put... So now our buffer looks like 485 A's, then a return address, then a buffer, or then our shellcode, and then our C's. So let's type that out. Let's split this pane in two. Let's do netcac tech NLVP. Did I use 4444? I did. I used 4444. 4444. And we're going to see if we get a reverse shell when the shellcode executes. Alright, let's make sure that the program is listening. It's not. We have to make it listen. There we go. By the way, this song, for whatever reason that's playing, this song is all Lovecraft references. This guy is rapping about Lovecraft. Various Lovecraft stories. Okay, we're setting the breakpoint again, so we should hit our breakpoint when this executes. Okay. We do hit our breakpoint. So we're at a push EXP now. Sub7 Photo, thank you for the follow, my friend. Cthulhu Fatagan, good to have you. We're going to continue on. And then we're going to ret. And now, you see, we are at the beginning of our shellcode here. This is the beginning of our shellcode, chat. So now, if we just hit play, we should get a reverse shell. Except, that's not what happens. We got an access violation when writing to some memory address. And then, if we go back to our Kali, we get no shell. What madness has occurred here? What has happened? We've been jebaited. We've been jebaited, chat. What has happened? Which fit deck am I using? It says www.fitdeck.com on it. So, yes. So what is happening here? So the first thing that is happening is that if we just look at can we look at the shellcode in memory? It probably is not, we can't really see it. Yeah, see, it's all a jumbled mess of instructions. You can't really make a sense of, again, the shellcode begins with a decoder stub, and in order to decode its shellcode, in order to decode the shellcode, the decoder stub needs to figure out where it is in memory. It needs to do it executes a few instructions that are able to figure out where it is in memory. And in order to do that, you remember I mentioned the floating point registers way back in the PowerPoint presentation when I talked about the different kinds of registers? There are floating point registers too that help with floating point variables and operations, and it's using a common hack using the floating point registers that allows it to get its current location in memory really quickly. It's using an instruction called FNSTENV to get its location in memory. And in order to do that, it pushes a whole bunch of shit onto the stack. In order to execute, are the floating point registers within scope for OSCP? Actually, absolutely they are. Absolutely they are. They're used, again, I'm not doing this consciously. msfvenom is just doing this. And this is just something msfvenom does. This is an msfvenom thing. Okay, so FSTENV, in order to figure out where it is on the stack, pushes a whole bunch, where it is in memory, pushes a whole bunch of shit onto the stack. And because our shellcode is located on the stack, and EIP is located in the stack, the shellcode is corrupting itself. It is corrupting itself. So how do we fix this? There are two ways. There are two ways to fix this. The number one way is by Purple Fox, is what Purple Fox is saying. Add a bunch of NOPs. Add a bunch of 90 instructions, 90 hex values. That is a NOP instruction. N-O-P, NOP. A NOP instruction is like, it's a no op, it stands for no operation. It just means that it's just going to continue on to the next, the CPU is just going to continue on to the next instruction. And it's going to keep doing that until it hits something that isn't a NOP. This is the meaning of the term NOP sled. If you've heard the term NOP sled, what it means is a whole bunch of NOPs put together. Let me see if I can find one in here. Let's look in View, Executable Modules, WarFTP. Search for command NOP. Here's a NOP right here. Here's a NOP right there. That's only one NOP, but like, you see what I mean? If there were more NOP instructions don't do anything. All it does is that the CPU moves on to the next instruction. That's all it is. So a NOP sled is like a long series of 90s meant for padding. It's meant for to pad it. So you can add a NOP sled to this and it will work. Another way to do it is just to recognize that when EIP and ESP are really close together, like when you have to execute a jump ESP to get to your shellcode, when EIP and ESP end up exactly identical. And the problem with that is shellcode tends to corrupt itself. So a simple way is just to move ESP away from... another thing you can do is simply to move ESP away from your shellcode. So you can just... I'm not going to show... I can show them both, I guess. So you could just... There's two ways to do it. So... We could go to, let's do which metasm. Okay, there's a tool called metasm that lets you. Holy shit, Nightmare coming in with 5 more gifted subs. Thank you so much, my friend. Cthulhu Fatagan. That's so kind of you. Although I have to admit, you've been outspent today, my good friend. You've been outspent today. Who was our big Cyber Insecurity gifted 50 subs earlier, my friend. So you are out of your depth today, I'm afraid. All right, let's do a quick battle in Stream Raiders before I forget again. This monitor. There we go. Now is Metasm still in here? Metasm. I think it's called Metasm RB. Is it Metasm Shell work? Which Metasm Shell? .rb? Nope. Tools. And Metasm is not in here. Can we rewatch streams through? You absolutely can. Just go onto my channel page, and you can see the videos. Just look in the videos. Locate Metasm shell.rb. There it is. This is what I want right here. Paste that in. So this will help us write our own shellcode. We're gonna write some really quick write our own shellcode. We want sub ESP, and I guess we can just go with 1,000. So we want to subtract 1,000 from ESP. This is gonna decrement ESP. Okay. Wait, this is interesting. Yeah, we're just gonna move ESP down. Is all. The first thing we're gonna do in our shellcode is just move ESP down to get it away from EIP. And so we do see, unfortunately, that there are some null bytes in here. We do have to be cognizant of bad characters. So another thing so sub ESP 1000 is not going to work. But if we do add ESP, negative 1000, we do see there are no bad characters in here, boys. No bad characters here. So we need to put this shellcode in here. And again, you can do this with NOPs as well. Okay? You can do this with NOPs as well. It is perfectly okay to do this with NOPs, but you need to get EIP away from ESP somehow. I just prefer it this way because I find NOPs too basic. I guess I'm just a special snowflake. Alright, so we'll vim exploit.py. And we'll do move ESP is equal to... I did it again with the quotes. Like that. And then we add the return address plus move ESP. This is too hard to read. Get rid of this. There we go. Move ESP plus buff, and then we have to subtract the length minus length of move ESP minus length of buff. Oh, I have an extra plus. Okay. Okay, now let's do this. Okay. Let's start the program again. Delete. Control F2. F9. Program's running. Let's set our breakpoint so we can step through. We set it. And now let's execute the payload and see what goes right or wrong. Python 3. I fucked it up. What did I fuck up? Did I forget a closing parentheses, perhaps? I don't think I did. What did I mess up? What was the exact nature of my error? It says invalid syntax. There's a space in buffer. God damn it. I can't read with this thing over to the side. There we go. Alright, what did I mess up? Space at move ESP. I don't see it. What am I missing? You guys are probably like screaming at your computer screens. It's 4-5 minus length move ESP minus length buffer. After return ADR. Up here? Oh, over here. Oh! Oh, okay. Yeah, thank you. Sorry. There you go. You guys are probably screaming at your computer monitors. Sorry about that. That's frustrating. Alright, we set our breakpoint. Alright, let's make sure we hit our breakpoint. We did. So let us step through. We return. And so it we see that it says it's confused about like what the instruction is. Did I mess something up? I think I messed something up. I think I see what the problem is. There needs to be... I'm forgetting the 4 C's. There's 4 C's in there, and I'm forgetting those. That explains what the problem is. Okay. I messed up. I forgot the 4 C's. Doing these in front of an audience is much harder. Okay, so it needs to be 485 plus the return address. Let's make sure the return address is correct. It should be. It's got to be because I'm hitting my breakpoint. So, and then plus, and then there has to be 4 C's. There has to be 4 C's before the move ESP. So, because we were seeing those on the stack earlier, and I kept meaning to add them, and then I kept forgetting. So we'll add some C's. Times 4 plus move ESP plus buff plus B. Let's make these D's just to be a little bit clearer. Okay, I think that should be correct. Move ESP plus buff plus, and then we pad the rest. Okay. Okay. I think that should be correct. Sorry about that. I kept meaning to add that. So what's happening here is that there are 4 C that the shellcode. So this is where ESP is right here. You see here? This is where ESP is, and our shellcode starts here. So it's confused. Because I forgot that there's 4 C's in between. I forgot that there's 4 C's in between our return address and the ESP. So you do need to add those 4 C's there. So let's restart this yet again. Doing these in front of an audience is much harder, I gotta say. And we'll control F2, F9, execute it, go. And now we will, you know, this time I'll go over here. Okay, got our listener. We send it. Now we should. Okay, that's actually good. So I forgot to set the breakpoint, chat. I forgot to set the breakpoint, and this time it didn't crash. Why do you think that is? Why do you think it didn't crash, chat? Because we got a shell, boys! Because we got a shell! There you go. Echo username. That's my username. We got there, boys. We got there. Now let's do it again. Let's do it again. This time, I forgot to set the breakpoint. We would like to step through it so I can show you what is happening. Okay? Thank you so much for the bits, Purple Fox. Thank you so much. So let me properly set the breakpoint this time. And I can show you exactly what occurred. Okay, Control F2, F9. Okay, it's going. Now let's properly set the breakpoint. And now we'll execute. We'll go over to our shell. We haven't gotten a shell yet because we hit our breakpoint, okay? So now we're at push. Now if you look up at the top left, you see push ESP and RET, okay? We're going to move one instruction at a time. Now the return is going to take us to ESP. And now we're at ESP. And now you can see our first instruction there. You can see the add ESP -3E8. That's 1000. 3E8 is 1000 in hex. So it is it's subtracting ESP. It's going to move ESP way the fuck up here. Way the fuck up. It's going to make the stack 1000 bytes bigger and give Metasploit, the msfvenom payload enough space to decode itself in memory. So now you'll see it decode. You'll actually see it decode if you hit. See, watch. So you're gonna see. Look. See, it's in a loop right now, and notice how the instructions are changing. Do you see how the instructions are changing? Do you see that? The shellcode is and now they make sense now. The shellcode is decoding itself in memory. It is decoding itself in memory. Okay? And now, so if we just hit F9 and continue, now the program is running, and we have a shell. We have taken control of the execution of this program, and have gotten a reverse shell. Which way is best? Neither. I mean, I'm firmly of the opinion that if it works, there is no, it works, it's good enough, man. I think this is cool. Honestly, I like showing my my slightly elevated mastery of assembly by just doing a slightly more complex instruction. But if you pad it with NOPs, it will still work. In fact, I can show you that. Let me just show you that real quick to show you what it's like to pad it with NOPs instead. So you only need to include like 10 or 20 of these, honestly. You don't need that many of them, is the point I'm trying to make. So you can include as many of these as you want. It will not, all they are is, we're just producing a NOP sled, and I'm going to show you what it looks like in memory. There we go. And that shouldn't change anything. That should be fine. And now if we can go ahead and start the program again, and we can do this one more time. And I can just show you what that looks like in memory. There's no better, it's not a superior way to do it the way that I did it. I just knew that people were going to say NOPs, honestly. I knew that people were going to recommend NOP sled, and so I was just going to show you a different way. just to help improve your understanding of what's going on, hopefully. So we do see that the process has terminated because we killed it. We killed the shell. So we delete these two and we start it over again. It's running. So now we need to set our breakpoint. Let's not forget to set the breakpoint. Execute. We have not gotten a shell yet. That's okay because we were at our breakpoint again. So we're at the breakpoint. We go through the push ESP and the RET. And now notice that we've ended up at a long slide, at a slide of NOPs. This is what's called a NOP sled, chat. Now notice as I execute each one of these, like nothing is happening. Like all the CPU is doing is just proceeding on to the next NOP. Like this. And so you can see also the FNSTENV instruction that I told you. This instruction pushes a whole bunch of shit onto the stack. So you just need to make room on the stack for that. So, but this is going to work, watch. See, watch, now the payload is decoding itself, see? The payload's decoding itself again successfully. So if we just hit this, we get our shell. There's our shell again. Easy, right? Now, was that so hard, chat? Was that so hard? Does everyone following? Does anyone have any questions about what was just seen? About what madness was just? But do I got root? Well, I'm a local administrator on this Windows XP machine, so yes, I do have root. I have to go now, but I'll finish the VOD. Gear Zero, thank you so much for coming, my friend. Cthulhu Fatagan, it's good to have you here. We already have root. This is root. 3 hours to exploit buffer overflow and get a shell. Honestly, I could have done it in probably less than half an hour. It's the painstaking effort of making sure everyone follows me and understands. It's not a race, honestly. If you can get the shell, you get the shell. Now, chat, who wants... Now, I know you're all expecting me to end the stream here. But, however, I did allude to some bonus content. Chat. Some bonus non-OSCP content. Now, if you want to turn your brain off here, if you're an OSCP student, all you want to know about this stuff is OSCP, and you want to draw the line there, what we're going to talk about right now is not a part of OSCP. However, it will be a part of other possible offensive security certs you could do in the future. So, do you recall that when we sent a buffer of 1200 bytes, we were using, this one was a buffer of 1100 bytes, chat. I'll show you. Vim crash.py. So this one was a buffer of 1100 bytes. But if this one, okay. So, this one is a buffer of 1100 bytes. Do you remember that when we sent a buffer of 1200 bytes, some weird shit happened and it crashed in a different way? Do you remember that, chat? While setting breakpoint, should we focus on ESP? No. You can use any register in which there appears part of your attack string. There were multiple registers, I think ESI and EDI both were pointing to part of our attack string. You could have used ESI or EDI as well. It's just ESP gave us the access to the most buffer. And it's very common to have ESP overwritten in this kind of a buffer overflow. Did 1200 bytes overwrite libc or something? No, it didn't. What it did was the program stopped accepting bytes past a certain amount, so it crashed in a different way. It created an exception. And let me demonstrate. Let me show you. We'll go back to crash.py, and this time we're just going to send 1200 A's. And I'm going to show you what I neglected to show you before. Now, this is the bonus content, okay? This is not OSCP. OSCP will not cover this. Bredaza89, by the way, thank you so much for the subscription, my friend. Thank you. Welcome to the Alhaz Red Team. Good to have you. So... But this will teach you more about binary exploitation, okay? there are more things to overwrite on the stack than just return addresses. There are other addresses on the stack that can be executed. So let's look at them. Let's find out. Let's look. Let's see it. Let's see it. So we're gonna execute this. Let's go ahead and restart this yet again. Now you might say this is pointless because we've already exploited this program once in one way, but for our learning, I think it is necessary to do it a second way for our learning purposes. So we hit F9 to start it. FTP, poor beleaguered FTP, is doing just his best, doing his best. Okay, so we're gonna do now Python 3 crash.py. Okay, now let's see what happened. So now we see, once again, we have an access violation, but but it's completely different. We're writing to 00B0000. Strange, and it seems there's no 4 1s in our EIP. Our stack is in a completely different place. Like, what's going on here? What's happening? What is happening? So what happens is that we sent so much data that the program what we do see. Well, let me show it to you this way. Down here it says access violation. Use Shift F9 to pass exception to program. So why don't we do that? Let's press Shift F9 and see what happens. Looky there. What's in EIP now, chat? What is in EIP now, chat? How interesting! How interesting! Codename Root, thank you so much for the follow, my friend. Cthulhu Photogin, good to have you here. What madness has occurred here? We passed it an exception, and we have 4141. We have our A's now in EIP. What has occurred? I made some extra slides just for this purpose, chat. So let's go. It did not save my place, so let's go all the way to the end. The structured exception handler. The lunacy, the cosmic lunacy of the structured exception handler. What fresh frontiers of madness await us? What mountains of madness have we landed at here? So, what is SEH? The structured exception handler. These are shorter slides, by the way. There's only like 6 slides. I am sure you have encountered the structured exception handler before, my friend. It's this. When one of your Windows programs says it has encountered a problem and need to close, that is the work of the structured exception handler. The structured exception handler is the way that an operating system handles exceptions. If a program generates an exception, as in it has an error or a problem, it goes to something called the structured exception handler to figure out what to do. In some cases, to pop this box up and ask you to send an error report, etc. Okay. So, if you're a programmer, I'm sure you're familiar with the try except block. What you're essentially doing with the try except block, when you're doing exception handling, is creating an entry in the structured exception handler chain, which we're going to talk about here in a minute. Most, if not all, programming languages have some form of exception handling. But sometimes programs don't handle exceptions at all, and they just use Windows' built-in exception handling. And that would be that's this. This is Windows' built-in exception handling right here. So here's the SCH chain, much like the meme chain. Each SCH entry consists of 8 bytes. It's a 4-byte memory address to the next SCH entry in the chain, and then it's another 4 bytes, which is an address to the actual SCH, or to the actual SCH function. Okay? So in this way, Okay, so when an exception is encountered, Windows will go to the structured exception handler of the process thread to figure out how to handle it. So it's going to look for the first SCH entry up here at 4chan, and it's going to see, hey, is this entry in the structured exception handler able to handle this exception? If it's not able to handle the exception, it will go to the next entry in the chain and try that. And it'll continue down the chain until it finds something that handles the exception. Okay? And if it doesn't find something to handle the exception, you get a blue screen of death, by the way. That's the blue screen is the last entry in the structured exception handler chain. If upper bounds on process memory are reached without finding a valid SCH entry for the exception, the program exits with a very well-known error text box. And if that fails, the blue screen happens. Alright, so here's what it looks like visually. So here's the stack. Here is the stack. And then, this is one entry, this is the top entry in the structured exception handler chain. The first 4 bytes are the pointer to the next record. Notice how it's a memory address of the next record in the chain. And then the second 4 bytes are the memory address of the actual exception handler program. So it's going to go, so when it encounters an error, it's going to check this function and see if it's able to handle the error. If it's not, it's going to come back here and it's going to go to the next entry in the chain. It's going to try that function and it's going to continue until something handles the exception. Okay? Is everyone following me on how the structured exception handler works? Why do we care? Oh my god, who the hell cares? Why are we back in the slides again? It turns out that in addition to return addresses and saved registers, the stack also contains pointers of the structured exception handler chain. So so if you overwrite these and the program encounters an exception,
such as if you enter too much input and the stack is overwritten,
then the execution will go to the structured exception handler to execute it. And since you have overwritten the structured exception handler, you can then hijack execution that way. Does that make sense? Yeah, if you have driver derps, yeah, but userline programs rarely trigger blue screens. That is correct. War-FTP would not generate a blue screen. President Zaki, thank you so much for the follow, my friend. Cthulhu Fatagan, good to have you here, my friend. So, is everyone following me on why this is relevant? Vowel Bus, thank you so much for the follow, my friend. Cthulhu Fatagan. So, here's a mitigation strategy for SCH. Windows is aware of the danger that SCH poses, so they have what's after Windows XP Service Pack 2, which means since we are Windows XP Service Pack 3, we're going to have to possibly contend with this. So safe SCH is implemented. Basically, programs compiled with a safe SCH provide the linker with all the valid memory addresses of their SCH entries. So if you overwrite one, it's going to throw an exception that you can't handle, because the address that you overwrote is not going to match one of the linked list of SCH entries that were generated at compile time. Windows will check if an address is valid before loading into EIP. So, we're screwed, right? No, we're not screwed. So all essential Windows components are compiled with safe SCH. But third-party programs,
like WarFTP,
are not required to do that. So, and oftentimes they will not do it. So, fortunately, WarFTP is not compiled with safe SCH, so we don't have a problem. So we must, when exploiting an SCH overwrite, we must look for memory addresses with non-safe SCH modules to which to redirect execution. Alright, and there's my sources. There's my sources. Let's get the fuck out of here. Get the fuck back in the debugger. Okay. Alright. So you can overwrite the exception handler to our handler. Yes! That's exactly correct, Ong31D. We can overwrite the structured exception handler to think that it's sending execution to a way to handle the exception it's just encountered because we sent it a whole bunch of crap. But instead it's sending it to our shellcode. Cool, right? Is everyone just like aching to view this cosmic lunacy that we're about to view here? Okay, let me crash this program again. Let's crash the program again, and I can demonstrate what I mean a little bit more clearly. Alrighty. Where are we with our battle ready in 1 minute? We might as well start the Stream Raiders battle before I forget again. Alright, so I have gone ahead and restarted the program. It is running again, and we're going to execute it, and I'm going to show you what's happening to SCH. Okay, we've crashed it again. So we have the weird access violation again. So if we go up here to view, and we go there's an entry for SCH chain up here with the ice wall prevent troop movement. Those aren't ices, those are crystals. I think those are actually beneficial to walkover, actually. DM Loken. Okay, so notice this is the SCH chain. This right here is the SCH chain. Make it a little bit bigger. So notice that SCH has been overwritten with A's. SCH has been overwritten with A's. EH and SCH is exception handler. Yes. Structured exception handler. That would be a self-contained ROP exploit, right? Not really bypassing ASLR, just not using any library OS code. Correct. We are going to execute a very simple ROP chain to deal with this, and I'm going to show you what that means. We'll get to that. If the word ROP chain scares you, there is a, it is a very simple ROP chain is required to do this, and we're going to go into that. But if the word ROP chain scares you, just forget about it. Like, just forget I said ROP chain. Okay, forget I said ROP chain. That's a discussion for another day. A full discussion for another day. I guess it wasn't a ROP chain I made with Mona. It was technically a ROP, yes. It's just only one ROP. We'll get to that. I'm jumping ahead of myself. But see that we have overwritten the structured exception handler. Does everyone see that? Good. Got to sleep soon on 3.1D. That's fine. It'll be up. The VOD will be up. Okay, so now we know what we need to do. What we need to do is the first thing we need to do is obviously overwrite. Is obviously do the pattern create again. Okay, we're gonna do pattern create over again. Does everyone remember pattern create? Our good friend pattern create. Let's copy Python 3 crash.py. Let's copy crash.py to sch.py. Vim sch.py. Let's do msf tac pattern create. And we're going to do tac L is 1200 bytes this time. So we do get our pattern again, and we're going to see which particular bytes are overriding SCH. Just like we did before, nothing has changed yet. Nothing has changed. We're just seeing what bytes have overwritten SCH. Buffer equals. Okay. All right. Let's do Python 3 sch.py. And let's go ahead and start this program again. And we're going to do F2 to restart it. How do you know if you got gifted a sub? It shows up on my Streamlabs software here. Like my streamer software, it shows up on there. There's been like 80 subs gifted. There has been. Yeah. Cheese Wads, you probably got a sub because like a guy gifted like 1 million. There's been like you said, it's been around 80 subs. Like seriously, no exaggeration. It's been about that many. People are just so goddamn generous today. I really do appreciate it. Okay, so let's it's running. Okay, everything seems to be okay. Now let's go ahead and let's send sch.py. I forgot to add the B. So we have to add a B for bytes right there. Very common for me to forget that. Okay, we've crashed it again. We do see it. We do have let's view the SCH chain, and we do see that the so recall that SCH entries consist of 8 bytes. Okay, every SCH entry is 8 bytes. the first 8 bytes, which is this 8 bytes, is the address of the next handler in the chain. This, the second 4 bytes, I know they're upside down here, but that's because of the stacks orientate. That's because they've just decided to orient it that way. But on the stack, you'll see that that they're oriented the other way. It's just confusing. This is the address to the actual structured exception handler, like the actual handler function. So this is the address we're concerned about here, 41317441. So let's head back over into Kali. Oh, my music went off again, so let's turn it back on. There we go. Back to Kali. So we're gonna do MSF pattern offset tac L. We don't have to do the tac L. We can do tac Q. 41317441. 41317441. Exact match at offset 573. Okay? So that means 500. Now, we have to remember, we have to put this into context. Let's bring the slides back up again real quick so I can just demonstrate this. So this means that this address right here, pointer to exception handler, this one right here, the pointer to the exception handler is what this address is. So 573 bytes in, that's what's being overwritten. There's another 4 bytes right before that, at 569, at offset 569, that is also being overwritten, but that's the pointer to the next SCH record. We just need to account for that in our shellcode because it's going to come into play later. You're going to see it's going to come into play later. Okay? Chill Step is a godsend to stream. It really is. I love these lo-fi, like Halloween-oriented, vibing music. I fucking love it. It's fantastic. And it's royalty-free. That's why I'm playing it every fucking stream now. It's really, really nice. Okay, so we have to account for that in our shellcode. Oh man, I missed President Zaki, codename Root, Volalbus, JVZ11. Thank you so much for the follows, my friends. Cthulhu Fatagan to all of you. So, when we're crafting our shellcode, so let's vim sch.py. We can get rid of this. We don't need this anymore. Okay. A times how many? It was 500 and we want to do 569. And I'm going to show you why that is in memory here. 569 plus B times 4 plus C times 4 plus let's add some D's as well, times 1200 minus 569. Again, I'm just padding the rest of it. This is all I'm doing here is writing a number of D's to pad the rest of the payload out. Minus 4 minus 4. And that should be correct. So let's restart the program again. Man, if it was more efficient to like this stream would have been like half the length, if it was just more efficient to restart this this program every time. Okay, so it's now listening again. The program's running again, so let's run sch.py. And now what we should see in the SCH chain is we should see 4 2s, these are our B's, these are the pointers to the next SCH chain, and these are our C's, the 4 3s are the C's, which we have overwritten. This is the pointer to the structured exception handler that will be executed. Is everyone following me? Oh, Ong31D, good night, my friend. Thank you so much. I'm really glad you enjoyed it. We got more to come, so make sure to check the rest of the VOD. But thank you so much. It's great to have you here, as always. Does everyone see what's happening here? Let me show it on the stack. I can show it on the stack as well. Let's open up the stack pane. let's check out ESP following stack. We have to actually, so I also want you to note, let's pass an exception to the program, all right, to see what happens, and then we're going to see what happens to the stack when this occurs. So shift F9. So now note firstly that most of our registers have been zeroed out. All of our registers except for EDX have been zeroed out here. So we're not going to be able to do a jump ESP like we did last time. I'm definitely going to be rewatching this thing and taking proper notes. I'm glad to hear that, Paperboy Gold. Like, I'm here to teach you guys. I hope you guys can get the most possible things out of it. But notice the rest of these registers have all been zeroed out. This is unfortunate. So we're not going to be able to do like a jump ESP. We're going to have to do something different. But let's see if we can, let's follow ESP and stack. And we do see, if, let me double click this. Okay, so here's where ESP is. And then now note that just 8 bytes down on this, on the SCH, just 8 bytes down, 8 bytes up. Well, it's 8 bytes up. It's a 8 bytes higher memory address. But notice right here on the stack, this is our attack string right here. This is pointing to our attack string. So that's an important thing to note. So now, let's go to our. Can we follow this in dump? Okay. So now see, I followed it in dump so you can see it a little bit clearer. So here's our B's. So here's all of our A's. Here's our B's, and here's our C's. And then these are being pointed to just 8 bytes down in the stack. There's a point just 8 bytes up in the stack, 8 bytes deeper into the stack from where ESP is. There's a memory address that points to this. I'm gonna dip here, Alhazra. This is so much good information. Help me understand this topic a bit better and grasp how to approach these. Looking forward to the rest of the VOD. Nitsuku, thank you so much for being here, my friend. Cthulhu Fatagan, you have a good evening. So you could search for jump ESP plus 8? Potentially, yes, but there is an easier way. And it turns out that many people have accounted for this. And this is a very common thing with SCH exploits especially. Having your shellcode 8 bytes up in the stack is extremely common. In fact, that's pretty much always how it works out. Okay? So what we need to do here is, oh man, my throat hurts. Whew. All right. So what we need to do here is find a way to get ESP to point at this instead. So we can, do you recall back in our slides? Let's go back into the slides. Here. This instruction and this instruction. POP-EAX loads the value from the top of the stack into the location specified in the operand, then increments ESP. It increments ESP by 4 bytes. And then RET transfers program control to a return address located on the top of the stack. That means at ESP. RET will load whatever address is in ESP into EIP. And whatever address is at the top of the stack will be loaded into EIP by RET. So what we can do here is we can execute 2 POP instructions and then a RET. And what will happen is these 2 addresses will come off of the stack into registers. It doesn't matter which register they get popped into. It really doesn't matter at all. What matters is they come off the stack. Then ESP will point here, and then we can just do a RET, and then EIP will jump to the beginning of our Bs. Is everyone following me? Is everyone with me on this? So the instruction we need to execute instead of jump ESP is POP-POP-RET. This is a very well-known instruction set. In fact, Mona has accounted for this, as we're gonna see. But I'm gonna show you once again how to search for these things manually. So we can go to View, Executable Modules. You want to always, again, as I said earlier in the stream, you want to always try and choose either a code that belongs to the program you're exploiting. So either WarFTPD or WarFT or this DLL that's part of it would be ideal. But let's go to search for sequence of commands, and now we can do a POP R32. Now R32 is a regex that will match any register, any 32-bit register. So it doesn't matter what register we pop into as long as it's not ESP. As long as it's not ESP, it doesn't matter what register we pop into. We want to execute 2 POP instructions and then a RET. And we do see we immediately find one. There's a POP EDI and a POP ESI right here, and then followed by a RET. Unfortunately, these have bad characters in them. Does this exploit hold true for Win 10 as well? Absolutely it does, yes. I mean, Win 10 modules are going to be compiled with safe SCH, but if you can find a driver or a third-party program that's not compiled with safe SCH, then fuck yeah, it'll work on Windows 10. Hell yeah. It's going to be a 64-bit exploit, but the same principles hold true. So this exploit has a null byte and a 0 and a 4-0. Both of those are bad characters, so we can't use this. Fortunately, Mona has our backs as usual, so we can do attack Mona, and we can do Mona SCH, and we can do CBP, which is characters bad, I think. Is that correct? Is that Mona? Let me just look it up. Let me look it up real quick. Is it CPB? Is that what it is, TMH Pwn? I'm just going to trust you blindly. I'm going to trust you blindly. CPB. And then you have to add your bad characters. So we can do X00, X40, X0A, and X0D. So Mona is searching right now. It looks like it succeeded, so let's check it. Yep, it looks like it found a whole fucking bunch of them, a whole bunch of POP-POP-RETs. So let's check our log. Here it is, and now we can do font, and we can raise it to like 20 or so. Okay, so you want to look for modules that are compiled without safe SCH. It looks like the only modules that are without safe SCH are WarFTP itself. And MFC42 DLL, that DLL, which is included with WarFTP. It's a WarFTP DLL. So as we pointed out as I pointed out in the slides, Windows XP Service Pack 3 was the first operating system from Microsoft that was compiled with safe SCH on all of its essential Windows components. So we want to find a POP-POP-RET that's in one of these modules right here. That should be easy enough. So we can use, I mean, this one right here will work. Right here at the top. This sumbitch right here on the top will work. Are poisoned safe SCH possible? What do you mean by that? Or spoof them? If there is, that's beyond my pay grade. Safe SCH kind of stymies it. But maybe someone much smarter can speak on that rather than me. So this looks fine. No bad characters. Mona should have checked for the bad characters, but it's good to check. This is a POP-EBX, POP-EBP, and a RET. This will work just fine. This will work just fine, chat. So let's look at this address. Let's copy that, and let's load up the CPU thread again. Let's search for that address in memory, and we do see there's a POP-EBX, POP-EBP, and a RET. So and there's no bad characters in it. This will work just fine. Monkey fucking a coconut, sir? MFC? Is that you, MSC? Okay. Alright, so we found an address that'll work for us. So let's restart the program again. Okay. F2. F9. Start it up. And, alright. So we're going to set a breakpoint for that. POP-POP-RET. Breakpoint. Okay. So we set a breakpoint. Program's running. Let's head into Vim. God damn it. Let's vim sch.py. Now, instead of our C's, recall it is our C's we are overwriting. Instead of our C's, we want to include this memory address. But recall, endianness is a thing. Endianness is a thing. So we need to reverse our bytes, the bytes here, to account for the little endian format. XCA, X80, X45, X5F. Okay. Now we can delete this. Now once we execute this, it's going to encounter the same exception as before. See? Same exception. But if we go to SCH, we view the SCH chain, we do see that the structured exception handler is pointing to that address. It's pointing to the address that we just put in there. So let's we can go ahead and pass an execution to this. We can go ahead and pass an exception to the program, Shift F9, and we see that we hit our breakpoint. We are now at our breakpoint with POP-POP-RET. Now, I'm going to make the stack pane bigger. I want you to watch really closely what happens to the stack as we do this. Okay? As I execute the next 3 instructions, I want you to watch the stack pane in the bottom right down here. Okay? Alright? So, pop. Now notice, that top address came off the stack. It came off the stack, and it went into EBX. It went up here into EBX. Okay? And now we're going to do it again. Pop EBP. So watch the base pointer. Watch EBP here. So it came. So that next 4 addresses came off the stack, and now it's in EBP. And now this address right here, and we end up at our B's. We are now in our B's. So we can execute code, chat. Code. If we just put code at these B's, it will execute. The 4 2s are the B's. Those are the 4 2s. Does anyone see any problems, though? Does anyone see any concerns with what they... Does anyone have any concerns with what they're seeing here? Oh, did someone see Star? Did you see Star? Was she behind me? Fish Not Fish and Purple Fox are correct. So, the issue we're having here is we have 4 bytes of code before we hit our return address. Like, so we can execute code, but this return address obviously can't change. This is the return address that we put into the code. We can't change that. So, we have only 4 bytes of space to execute code in. So what do we do now? Are we just screwed? Are we just fucked? Like, what do we do? Like, I'm lost, chat. Tell me. Tell me, what do we do? What? Purple Fox, Purple Fox once again is correct. So, we can execute, 4 bytes is more than enough bytes to execute a little bit of a jump. Purple Fox is even putting the fucking assembly in there for me. He's a madman. He's a madman. Okay? What he's saying is we can put in assembly here for a short little hop, so that we will move the instruction pointer down here into our D's. Into our 4 4s, into our D's, and there is plenty of room for shellcode in our D's. Does that make sense? Is everyone following that? So we need to execute a little tiny bit of shellcode in these 4 bytes that will just hop right over this part of memory into this area of memory, so we can execute. We can just throw our shellcode into our D's. Can I elaborate on the jump sum? Absolutely, I can. Absolutely, I can. So, I believe a jump is EB. My good friend Purple Fox is helping me out with that. I think it's EB, and then we would want to do, like, we could jump, like, 6 bytes, probably. 6 bytes would do it. So, so if we go into... We can restart the execution of the program again. So let's restart. Let's go into here. Delete. Okay, Control F2, F9. Where are we at? Stream Raiders. We're at 3 more minutes. This is kind of an involved battle. I'm going to give it the extra 3 minutes, chat. I'm going to give it the extra 3 minutes on Stream Raiders. Okay. 3 more minutes. Get your units in. Get your units in. It's a boss fight. Big battle. Big rewards. Alright, so we're listening there. And then we can... so I think... okay, so it's going to be... If I could have actually before I restarted it, I should have just altered the assembly in the debugger. In the debugger, you can edit the assembly to change the code that's being executed. That's what I should have done. But it'll be fine. I'll just demonstrate it this way. So vim sch.py. So here in our B's right here, these B's need to change. They need to be B. An X, and it's EB. A short jump is opcode EB. That is the hex opcode for the short jump. And then we're going to jump just 6 bytes. We're going to jump 6 bytes. And then we'll just change these B's into NOPs. It's bothering me. Change these B's into NOPs. And then 2 more NOPs. Now notice... These are only 2. These are still 4 characters, but now one codes for a short jump, and you're gonna see that in the debugger when we get in there. And one codes for one is just NOPs. These NOPs won't be hit. These will not be hit. This is going to jump 6 bytes in the future to here. It's gonna jump 6 bytes down in memory to here. That's the plan, anyways. Okay, so let's set a breakpoint. I don't think I set the breakpoint. So let's set the breakpoint. And you're going to see this execute in memory, and it's going to be like magic. It's going to blow your mind. All right, here we go. We get it there. We did it. All right. So we hit our breakpoint again. Or we did not hit the breakpoint just yet, but remember that we need to pass an exception to the program. So F9. We hit our breakpoint. We do our POP-POP-RET, and now you'll see that the first instruction here is no longer B's. It is jump short. And then 00F. So if we execute that, it's not 00F. It's jump short to this address. This address is down here. So if we execute that, we notice we end up right at the beginning of our D's right there. We did it. So we can just throw shellcode in there, and it will work. And the best part is, chat, remember last time we had to do that thing where we moved ESP. We moved ESP away from EIP. We padded it with some NOPs, and we moved, we did it 2 different ways. I moved ESP away manually with a sub ESP, with an add ESP command, and I also did it with a NOP chain. You don't have to do that here, because notice that EIP and in ESP are not close together. They're rather far from each other, so we don't have to worry about that this time. So now we could just slap our fucking shellcode in there, and it's gonna execute like a motherfucker. The madman will just execute for us. So we'll do that. Delete these. Restart the program again. For one of the final times for this evening, I will say. Okay. Now we want to generate our shellcode. Okay, we have the same bad characters. The bad characters haven't changed. We're putting the payload in the same place. So we'll generate the same shellcode. I could just pull the shellcode out of the... I could just pull the shellcode right out of the previous exploit, but whatever. Alright, so we're just gonna copy that. Vim sch.py. Okay. There's our shellcode right there. And now instead of our D's, we're going to put plus buff plus D minus, and we have to subtract the length of the buffer. Buff. Okay. I think that works out. Now we do want to be cognizant of the length of our shellcode. The shellcode is 351 bytes, and we have a buffer size of more than that, so we're good. But there will be cases where you're gonna have to squeeze the shellcode. Okay, there's going to be cases such as in OSCE where you may run into a very restrictive execution environments, as in lots of bad characters or a very, very small buffer size, that kind of thing. That's where you got to get creative. And Purple Fox, once again, is preempting me. Egg Hunter is one option you have to solve that problem. But Egg Hunter, again, okay, remember when I said that a ROP chain, this POP-POP-RET instruction? Well, let me just get it back into memory and I can show it more clearly. Escape, stop. Okay, I think we're good. Okay, and now we'll restart the program again. Did we restart it? It looks like it is running. Let's hit the breakpoint. Okay, and let's go ahead and execute that. We go back in here. We need to shift F9 to pass the execution. We hit our breakpoint. Now this POP-POP-RET, I forgot to mention, this POP-POP-RET is basically a very small ROP. It's not a ROP chain because there's technically only one ROP in the sequence. But for those of you who have heard about ROP chains, this is what they're referring to. Something like this. A sequence of instructions that do something we want that end in a return, that end in a ret, which takes us back to the stack. ROP chains are a modern way of exploiting this kind of thing because they get around a certain mitigation. They get around a memory mitigation that has been implemented since this exploit came out, called data execution prevention. But that's a talk for another time. If ROP chains scare you, if the word ROP chain scares you, just forget I said anything. But for those of you who are interested in knowing what a ROP chain is, this is basically what it is. It's just only a single ROP. So we'll execute the ROP. We end up at our jump. We jump, and now notice our shellcode is executing. See? It's decoding itself in memory right now. So now, which means we should be able to go back over here. Oh. And now, we can hit that. And we have another shell. We've done it. We've exploited this program two entirely separate ways. Card from the fit deck. God damn it. I have so much fit deck to do. 6 fit decks and 6 pull-ups. Jesus. Okay, we'll get started on those in just a minute here. Is everyone... Okay, and just to prove to you that this exploit works without the debugger. Because it's so much cleaner when you do it without the debugger, right? So let's... We don't need Metasm anymore. Exit. It's so much cleaner when you do it without the debugger. So let me demonstrate. We'll close out of the debugger entirely. Open up War-FTP. I have to delete these two things again. Delete these. Start it up. So now we've got the debugger is opening, or so the program is running without the debugger this time. So let's now let's execute. And we see we have our shell. So it works outside of the debugger too. And I can prove that the other one works too. Back in here. War-FTP quit on us. I needed to just write a VBS script or something that removed these every time, because this is fucking annoying. Okay, here we go. Let's load it up again. And let's do... And I'll just prove to you that Python 3 exploit.py works. And we have a shell there too. Cool, right? Now, does anyone have any questions about what was just covered? If you didn't get it all, that's okay. The VOD is going to be up. I highly encourage you to watch the VOD and gain a heightened understanding. I'm really glad. Again, I've had a lot of requests, even just the last couple. I'm a local admin, like net user, net local group administrators. See, this is our username. I can prove that. Echo username. See, this is our username, and we're an administrator, so we do have root. Cool, right?